Thanks to everybody for coming. I think we can start, and also thanks to the Centro de Giorgi for the organization and the hospitality here. I will leave the microphone to the director of the center, Professor Andrea Malchiodi. Okay. Thank you.
Okay. Hello, everybody. So welcome to the meeting geometric methods in calculus of variations. I'm Andrea Malchiodi, the current director of the De Giorgi Center, and I will just say a few words about it and promise I won't take much time. So the De Giorgi Center was founded about 25 years ago, formally as a research laboratory of Scuola Normale, but with the goal of creating opportunities for the mathematical community of Pisa for gathering. So it's funded by Scuola Normale, but there is also a bigger contribution from the University of Pisa. Also some small amount from Scuola Superiore Sant'Anna and from Fondazione Sansone. So the main activities since the start of the center have been schools, workshop, intensive research periods. And we have visiting positions of two types. So there's an opportunity to do research in pairs or in groups. And we also have postdoctoral positions of 2 years with the opening in general in the fall and starting the year after. Basically, that's all I wanted to say. So I would like to thank the four organizers for bringing up this very interesting event, and the staff of the center also for their constant and valuable support. Thank you.
Okay, thanks again. Okay, we can start with the first speaker, Lia Bronsard from McMaster University, and she will talk about a new partitioning problem.
Thank you. Okay, thank you very much to the organizer for organizing this very nice conference. In particular, I love coming to Italy. This is just, so I'm so happy to be here in Pisa. As usual, Italy is so beautiful. It's full of colors. It's so warm. It's just so pleasant to be here. And it's not even hot. This is a very nice day right now. Much nicer than in France. So this is joint work with Stan Alama and Silas. So it's lots of work put together. Stan and Xingyang Lu and Chong Wang for the motivation to this partitioning problem. Stan with Silas for studying this problem. Most recently, I'm working with Mike. And even more recently, this is hot of the press, not even actually, it's working on. Some work with Mike, Robin Neumeyer from Carnegie Mellon and Anna Skorobogatova from ETH. Mike is from, actually moved now to Illinois, Chicago Technology of Chicago, Illinois. And what else? And if I have time, I'll finish with some conjecture with Dominic Stenteschi and our student, Tan. Okay, let's see. It goes this way. Okay. So also, I hope you will forgive me. Since I'm starting the conference, I thought it would be fine to do something very general. It's the beginning of the week, something that is not too technical, in fact, not technical at all. So let me start with very classical isoperimetric problem. Find the shape of given area with the smallest perimeter. So this was known, of course, to the Greek, but to be proven only in the mid-19th century by Steiner and Weierstrass, showing that the circle is the best shape for a given area. And then, of course, natural extension, one may wonder about, determine the optimal shape of a pair of planar region with given area whose combined perimeter is minimized. So this led to the double bubble conjecture that it would be the standard double bubble that uniquely minimize this pair of planar region. And this is a picture. This is in 2D. This is with Chong Wang, who was my postdoc. And this is from the web, the 3D bubbles. So these problems also come naturally when studying bubbles, soap bubbles. The difference here is same area, two different area, and you expect the chambers to be bounded by spherical or circular shape with 120 degree at the triple junctions. And this was proven in 2 dimension by a group of actually undergraduate students, Frank Morgan in 1993. I always find it amazing, very nice that some undergraduate students can really prove some important results like this. And they went on to in math. And the more difficult case, let's say, is in dimension 3 by Hodgkin, Morgan, Rittore, and Ross. Then, of course, this also the question, can you partition the plane in more than 2 or 3 shapes? So any number of shapes. So the triple bubble, I have a picture in 3D, so sorry, but the triple bubble in the plane, this was the thesis of Wishiramala in 2004, that he proved this triple bubble conjecture. Then you remember I was in 2 or 3 dimension, in any dimension, using different techniques by Richard, and I'm also mentioning Landlord, who also did the case. I will come back to this. Right now, the weight in front of the perimeter is the same, but you could have a weighted perimeter problem. Then very recently, Millman and Niemann, and they even have more result in recently, even more recent, they proved the K bubble conjecture when the total number of bubble is less than the minimum between 5 and the dimension plus 1. So, for example, their result, using again different techniques, proved the double and triple in all dimension. The quadruple bubble is proven for any dimension bigger than 3. And they also get some regularity result. As long as the total number is less than dimension plus 1, a minimizing cluster must have spherical interfaces. More recently, I'm also mentioning, because we'll come back a bit later, also because it's a very nice result, the quadruple planar bubble with equal area is also proven by Paolini Tortorelli. By the way, the shape of the quadruple planar bubble with different areas is still not resolved. And I will come back to that perhaps at the end with my conjecture. Then one can ask, well, is it in terms of partitioning problem? Just you divide into many areas or bubbles. So this is where my other work comes in. So these bubbles also come in the study of black copolymers. So maybe spend a little bit of time on black copolymers. I'm going to come very quickly to block copolymers, but basically this is what's called a tri-block copolymer, where you have 3 phases, A, B, C, that are attached but repelling. So the model is not just perimeter, there will be a non-local term in addition. And this is the physicists expect, depending on, there's many parameters in this model, depending on the choice of parameter, and depending on the area, think of area, the mass of each of these phases, A, B, and C, depending on the mass or the volume, you would expect lamellar shape if they have the same mass. And we're going to see at some point this one where when one of the mass is very small compared to the other 2, or here 2 masses are very small compared to the third. But you see there's even more complicated morphology for this. Local coming up, local, that's my perimeter term with weighted perimeter term. And this is the non-local term that is necessary in the model of black copolymer. And this you probably all know, but if you have different unequal surface tension, you would expect different angle at the triple junction, which the angle depends on the surface tension. Or in fact, this problem, let's see if I can go back. This problem, this first local term really comes as a limit of a gamma limit of a diffuse Canhillion model, for people who know this, with some some potential, and so this sigma ij really represents a distance in that energy landscape. But anyway, let me continue. So this surface tension here determine the angle in the case of unequal surface tension. And you can get, depending on the relation between those surface tension, you can see that because of this angle condition, basically, you can see different minimizer of this weighted perimeter. You can even have, in the case what I call degenerate here, instead of an annular region. And to get uniqueness, determination of what should look like this minimizer, the non-local term happens to be important. But again, I'm going back to the perimeter, which is what you end up when you zoom in around these small shape I showed earlier. So just to make again the connection, in the tetrablock copolymer, triblock copolymer I mentioned earlier, we'll see in a second, when you look at these small phases, some minimizer will be double bubble in two dimension. And you can also get triple bubble. This is my two-dimensional picture here. And you obtain them, again, as I said, when you take some of the phases are very small compared to the other. And then when you zoom in around this region, you would end up in this geometrical problem, the weighted perimeter problem. This is precisely the case of equal area and the case of different area. So now let's see if I can do this. Oh, wait. I wanted to show you something else. I must have forgotten it. Let's see if that was. Yes. So this is this full non-local problem, perimeter plus non-local. And you start with initial random initial data. In this case, you're going to have two small phase. So we expect double bubble. For the perimeter, there's just two small phase. It's equal weight, so you expect the equal area double bubble with 120-degree angle. And the effect of the non-local term is to have many of these, so they are broken into small pieces, and each of the small pieces satisfies this perimeter problem. And I'm letting it run because notice that eventually, yes, you do end up with double bubble. We are letting this, it's a gradient flow for the energy. But something that we cannot explain is still happening. As you can see here, eventually these double bubble line up. This must be some sort of second order gamma convergence or third order, and that we are not able to, we tried, but we're not able to prove this orientation preservation at the end. Okay, so and this was the case of unequal, and the case where you have more than two small phase, you could have three small phase, and that's when you end up with triple bubble. And so all these double bubble, triple bubble, quadruple bubble, all of them would come naturally in the limit of diblock or a multi-block copolymer, in the case where one of these masses are small. So these geometrical problems come in because when you zoom in, you get those perimeter problems. So this led to this new question. So far I mentioned two small in a sea of big one, three small, four small, always one big one, and two. And then we thought, well, what about if we had one small mass and two big ones? And again, you take this particular limit. So the mass is small, the appropriate limit to be able to see this geometrical problem, but split into many shapes, many bubbles. So this is the numerics for the non-local problem, right? I'm looking at non-local problem, one small mass, take an appropriate limit, and you see what happened is the two big mass form this lamellar shape we have seen a bit earlier. And the small mass, well, because we're trying to minimize perimeter, we'll want to adjust along the interface between the two big regions. And when you zoom in to see what the geometry of this small particle is, what you end up, I'm going to describe next. So I'm describing again how I get to this. I expect first, this is not actually proven that minimizer of the non-local tri-block copolymer energy from lamellar pattern for an appropriate choice, this interaction in the non-local term. With tiny droplets, so we are able to get, assuming this lamellar pattern, that this is some work with Chong and Xingyang Lang, we are able to get the fact that there will be tiny droplet align on this lamellar transition line. And then I do the blow up to figure out what is the geometry of these lens, of these bubbles. And when you blow up, what we expect to see, what we show, is that indeed what you get is not a ball, but really a lens. That's what will minimize the best this perimeter problem. So we recover a lens shape, or I looked up on the web how to pronounce vesica piscis. Of course, this is Latin. I got it in Italian. So anyway, I'm trying vesica piscis as my guess for vesica piscis, which is a well-known shape, actually. This is a circular arc here of a circle centered here, and this is a circular arc of a circle centered at the other edge with a 120-degree angle. This is the case of equal weight. This is all equal weight. So this, in fact, leads to this new partitioning problem I've been talking about. All the time before, you had several bubbles in the complement being Rn, or for example, Rn. Here, we have a situation where on both sides of this line, you have infinite area. So we now have a partitioning of my, let's say, R2 into two infinite region and one finite. And so this is the new partitioning problem, is having more than one infinite shape. This was, well, new. This was exciting for us, applied mathematicians, to get to pure math via this type of problem here. So the new partitioning problem is to prescribe one fixed mass in a sea of two different infinite regions. So now this is with Stan and our master student, Silas Vrian, we decided to discuss, to set up this new problem. So of course, we have to be careful because this has infinite length. So obviously the perimeter is infinite. So we're talking about locally minimizing perimeter. So we are introducing the notion of locally minimizing NM clusters based on, so Maggi, the book of Maggi's, Francesco Maggi's, very detailed. There's lots of information. It's rich. And so he, of course, had introduced clusters, but now we are introducing clusters with several proper chambers of finite measure and several improper chambers of infinite measure. So we call an NM cluster chi, which has two pieces, a pair of family, E and F, of sets of locally finite perimeter. So there's N finite and M, which will be infinite. So the proper chamber have finite area or volume, and the proper chamber of infinite. We associate, therefore, a volume vector to this locally minimizing NM cluster, which is what you would expect, right? Some finite numbers and several infinite numbers for the number of infinite areas. And so, for example, a double bubble cluster, the one that we're comfortable with, that there's lots of already proven conjectures, this corresponds in this notation to a 2-1 cluster, 2 finite, 1 infinite. You're prescribing 2 area in R2 or Rn. That would be the double bubble cluster. And now what do we need? But we mean for this generalization, the NM cluster to be locally minimizing. Again, we are dealing with things of infinite perimeter. So a locally minimizing NM cluster in Rn, it's basically with respect to compact perturbation, but compact perturbation for every ball here, and we compare to any other NM cluster with the same volume, so same number of finite infinite, whose symmetric differences in this compact set, the perimeter must be smaller than the competitor, right? So that would be our locally minimizing notion of an NM cluster. So for example, and then we study what is the solution to the natural minimizing partitioning problem. So for example, the 2-1 partitioning problem, finding the cluster that minimize locally with those given volume here vector is, so for example, we are comfortable with 2 finite y infinite. The 2-1 partitioning problem is resolved by the double bubble. And so coming from this diblock copolymer, or actually triblock copolymer, the 1-2, 1 finite, 2 infinite, with, let's say, area 1 and 2 infinite, is the problem we're trying to see what the bubbles look like around the interfaces. That's the problem we're interested in. And maybe going too quickly, any questions? Yes. Yes. It's also assumed that Rn minus the union of all this is empty. I mean, it is covering everything. Yes. It's a partition, exactly. So we work with Stan and our master student in R2. It's already good enough. The standard lens cluster, so this is with equal weight, is we have an explicit formula for the standard lens, which helps a lot. We have explicit given in area 1. We know exactly what the shape of this curve is. We can determine. We have all the information that are explicit. And so we were able to prove that this is called the standard lens cluster. We're able to prove that it is the unique locally minimizing cluster. For this problem, we're interested 1 finite, 2 infinite, with area vector 1 infinite. So we were able to prove not only the existence, but also the uniqueness, which is actually the hardest part. So we had actually first done this in the very calculus of variation sense, using, thinking of graph first. This is a master student, after all, using some symmetry. And at some point, Frank Morgan said, no, you can't prove this in general. You don't need graph and things like this. What he noticed made us realize, then one has to prove it, is that, here's the picture, it's the best, I think. Take your double bubble here that we know very well in 2D, and take this area, one area, let's say this one tends to infinity, then you will end up with the lens cluster. So his idea is that basically take this limit, you should be able to get the existence and uniqueness using the fact that there is uniqueness for the double bubble. So, well, to prove this, we had to prove that, right? That if you take a double bubble and you take the limit in some appropriate L1 log sense, it does converge to, and this is the notion of distance we have to use. The double bubble does converge to the lens cluster, and we have lower semi-continuity. So, and we use the corollary of the double bubble conjecture, where the double bubble is a minimizer even for larger area, to be able to prove that indeed this is the local minimizer. And this is the same picture, so it grown, so we see well. So we use very much on the knowledge we have here to be able to study this limit and prove this. The uniqueness is very delicate. Our proof depends on being planar and is based on very powerful regularity theory of Fred Holmgren, Gene Taylor, and Frank Morgan, using the fact that the interface are pieces of arc with same curvature and meeting at around 20 degrees. So we're really using the structure to be able to prove uniqueness of this lens shape. So at the end of our article with Mike and Silas, we made some conjecture on the 1-3, and if I did well, I was not supposed, I did not do it well. I wanted you to guess what should be the 1-3 shape. So we have 1 finite and 3 infinite shape. And I wanted you to guess, but too late. We get this, I call it, I mean, there's many names. We called it Taylor chalk, but this is Raylo's shape here, it turns out. This was our conjecture, but now I won't click. Can you guess what should be the solution to 2 finite, and 2 infinite? And I'm counting 5 seconds. Anybody? They are thinking. People are thinking, yes. That looks very good, actually. What you're doing with your hands look good. Do you have the courage to say it? No. Well, I call it the peanut. Basically, think of my third bubble going to infinity. That's one imprecise way of saying that. Yes. If I blow down this problem, I will end up to the plane. Exactly. Exactly. In 2D. This is in 2D. I'm going to come back to higher D. Very good. Yes, very good question. Yes. Blow down are very important. Yes. Okay, so this was proven recently by a paper by Matteo, Novaga, Paolini, Tortorelli. They studied this, they have lots of results. I'm just giving some result here. In particular, they have a very nice closure time in Rn under some assumption that the boundary between the improper chambers at infinity contains an n-1 half space. Under this assumption, oops, nothing's appearing. They are able to, because of this closure time, they are able to obtain existence of, and sometimes uniqueness in 2D of certain shape. Like this is, again, 3 finite, 2 infinite here, by taking just precisely this idea of blowing up one volume. And we have the quadruple bubble, for example, conjecture resolved by Millman and Niemann. So we do have this structure to be able to work with. So they have existence in, okay, I'm going to say, I was going to say number of shape, not quite. So they have existence as long as there's no more than 4, I mean less than 4 infinite partition pieces, infinite region. There's non-existence if there are more than 4 infinite region. They have uniqueness in 2D, but not in higher dimension. And I'll come back to this a little bit later. So with Mike Novak, we studied the case of weighted partitioning problem in any dimension. So, but again, 1 finite, 2 infinite. Okay? 1 finite, 2 infinite, that we know it's a lens in 2D. And we had uniqueness in 2D, but we are studying in any dimension. So again, 1 finite, 2 infinite, and this is just a weighted perimeter problem. And of course, you ask that this family of weights satisfy a standard condition, positivity, and the strict. Again, remember, I had the degenerate. It leads to something different if it's degenerate. We're assuming strict triangular condition. And so this is our result. The standard weighted lens cluster, again, I'm looking at the 1-2 case, is locally minimizing in any dimension. We do need to make a little bit of symmetry assumption against the infinite and finite partition. So, of course, up to rigid motion, the standard weighted lens is the unique, locally minimizing 1-2 cluster up to dimension 8. Because in dimension 8, there's always this option of using the Simon's cone to perhaps construct other locally minimizing problems. So we also have uniqueness in dimension 8, under a condition that excludes the possibility that the blowdown gives you is these Simon's cone. So we're assuming this, and it's written here. We're assuming this planar growth in dimension 8 at infinity, dimension 8 or more, in order to be able to get also uniqueness among locally minimizing 1-2 clusters. We obtain a stronger closure term than the one in the paper of Matteo and earlier, that I mentioned earlier. In the case of any number of bounded chambers and 2 infinite chambers, in the sense that we don't have any assumption on the limiting a behavior. And so this again allows us to construct always from locally minimizing n bubbles, n minus 1 and 2 infinite clusters from this closure term. And we also obtain classification of the asymptotic behavior of these n2 local minimizer. Again, for that, we need to assume particular growth at in dimension 8 and more. I thought I would not have time, but I think I have time to give a quick idea of the proof. To show again that the lens cluster, so weighted standard lens cluster, is the unique local minimizer of a 1-2 partitioning problem and dimension up to 7 for the uniqueness without the planar growth assumption. So this is just basically the steps. You need to show some volume density estimate so that the finite chamber stays bounded. What is very nice is that we show that the interface between the 2 infinite outside some cylinders here is the graph of a function that satisfies some minimal surface equation, and hence this asymptotic behavior. And this is some result that is based on some work on the exterior problems, monotonicity formula from Francesco Maggi and Mike Novak, and using Allard's regularity term. So this gives us a plane of symmetry for our 1-2 partitioning problem. And that's very helpful because that allows us to use some Steiner symmetrization inside this cone here to construct some competitor here. And using the fact that the only symmetric solution to the liquid drop problem above a plane is this lens. This is, in fact, in Maggi's book. So using the asymptotic behavior, that allows us to be able to study the difference between this symmetrization here and our possible minimizer. And then we are able to use some rigidity result to conclude that, in fact, the minimizer must be, the only possibility is the lens. Very hand-waving proof. So now let's go to our new result. So this is, when I say hot the press, it's even worse. It's actually in work in progress. So I'm taking chances here, but we are confident of what I'm presenting. We are able indeed to prove non-uniqueness for the 1-2 partitioning problem in dimension 8, in fact, by hand, literally, this is, and we'll see some other dimension. We're able to also show non-uniqueness. And it is based on, as I said, this Lawson, in fact, Simon, I said, but more generally, Lawson cones, which I recall or define here. Those are very important in our construction here. These Lawson cones are area minimizing with an isolated singularity in R. This K and L here is where what your spaces are. So K plus L must be bigger than 6 in order for this to be area minimizing with the isolated singularity. So it's dimension high enough that you get these. I'm writing specifically in the case K plus L equals 6, so we're in R8. The area minimizing Lawson cone are the Simon cone, C33, and C24 is a Lawson. So when it is symmetric, it's Simon, K and L, and otherwise it's Lawson. And then we need to introduce some quantity, which is very natural for the problem. So we will need to compare basically, if I can say very vaguely, the length to the Lawson cone. So we look at, think of a lens again. I mean, we've seen a few times, right? This piece of a sphere above the plane. So I look at the radius of the lens, the one of volume 1, intersection the hyperplane. And I look at the difference between the surface area, if you want, right, of the boundary of the lens and the piece on the plane. So in 2D, this would be the two arc circle minus the line. And we do the same now with generally with a hypercone. We look at the difference between this Hn minus 1 of the surface of the finite area minus in the case where you intersect with the cone. And we look at the infimum of this difference among clusters with this given finite area, and the boundary of the two infinite area must be intersecting the cone, right? Must be inside the cone. And we show that if we have a condition that this lambda c is less than lambda plane, we are able to do the whole idea behind this construction will be some sort of compactness approach by compensation. And more specifically, we look at this competitor here amongst Lawson cone. So we call lambda Lawson the inf of this, in a sense, rescaled, in a sense, normalized energy, if you want, because these perimeters are infinite, right? So we have to deal appropriately. So we're looking at this inf among all Lawson cone. And so what would be important is the comparison between lambda Lawson and lambda plane. And our results, so this is with Robert Neumeier from Carnegie Mellon, Mike Novak from now Illinois Tech in Chicago, and Anna Skorobogatova, who is a postdoc at ETH. And our result is, if you're in dimension bigger than 8, at any dimension, if these two quantity are lambda Lawson is strictly less than lambda plane, then there is a local minimizer of our original partitioning problem, such that if you take a blowdown, we're looking at blowdowns here, of one of the infinite phase, you take a blowdown, the blowdown is a singular area minimizing cone. There will always be some which is not just planar. We have some there is, yes, so it's for any sequence of blowdown, we are able to, no matter every blowdown, we find that the limit is. No, we're able to show that, so we don't know exactly how to characterize the limiting blowdown. Yes, we don't. We don't. Was that? The same. So we have some density comparison that is very helpful in the proof of and our result. So recalling the term that we wanted to prove that it's non-unique, that there is some lowdown that converge to something, a Larson cone which has smaller local perimeter. So in dimension 8, we are, this is a construction by hand, we are calculating these two quantities, and it's, we are certain, I mean, this is exactly calculable. In even dimension between 10 and 40, the formula is a bit ugly, so we rely on Mathematica, but it's still some nice formula involving hypergeometric. So again, we are totally confident of the result. In odd dimension, we are still working on it to be able to convince people, yes, it is, there's no error, numerical error. This is really what Mathematica is telling us is what is true. So non-uniqueness for the 1-2 partitioning prime in those dimensions here. And now do I have the courage? I think I do, because I have time. So, that forces me to do some conjectures. That's very dangerous. So now with Dominic Stanteschi, who was my postdoc and is now at Nancy as a maître de conférence. And we are sharing a student and co-supervising a student, Tan Huan. We decided to do some numerical work on the partitioning problem, the equal weight partitioning problem, 2D, but we can even do some 3D. Because as I said earlier, we know exactly in 2D, right, what it looks if it's two finite, it's this peanut, I called it. One finite, three infinite, I said this Taylor chalk, I call it Relos. But otherwise, we don't know actually what the minimizer look like. So we decided, let's do some numerics. And so this is 2 infinite, 3 finite. This is the initial data. The numerics we're doing is different than usual. It's we are kind of using, we are in a periodic setting, of course. We're not in infinity here. That allows us to use Fourier transforms. We're doing some sort of minimization problem with constraints. And this is the initial data. And you will tell me, well, that shows unsymmetric, you're cheating. So here is another initial data. And in both cases, what do we get? So you might be surprised. It's not the triple bubble, right? The triple bubble, it's not like that with 2 lines. No, it's this, I'm calling it caterpillar at this point. Caterpillar shape. Again, it's 120 degree. It's a piece of arc of circles. And so this was coming from the first initial data, which was symmetric. You tell me, oh, wait, so what? But we also did this on the right. And in that case, it's not finished, but we're going to get to the same caterpillar. So no triple bubble, end of triple bubble for the 2 infinite case. And now I'm getting more and more courageous, but there's time. What about quadruple, right? Quadruple bubble and 2 infinite, 4 phase, 2 infinite. Now I'm again, I have some time here, leaving the audience to think. What do you think should be the local perimeter minimization? 4 finite, 2 infinite. And remember, you may not know, but the result I mentioned for the quadruple is known in case of equal area. It is symmetric. 4, it's like a butterfly, slightly exaggerating. So, you want me to go on? Or you want to say something? I'll go on. You're concerned, right? You're concerned. Who? So here's the first. We decided we're always taking circles. Let's do something different so that something is obliged to happen, right? So we took 4 squares. A line, you'll tell me cheating again. So we also took this. So maybe this one will want to orient. I mean, with the quadruple bubble, I have more hope, you know, this symmetry. Maybe. Okay. So the left one went to my caterpillar. I like my caterpillar. I also like quadruple bubble. So my other one there went to, this, which is another option, right? Very natural option. Now, according to my numerics, I'll tell you which one is smaller perimeter, but I'll have you to vote. Who votes left? You have to raise your hand. Who votes right? You're all losing. But I have to admit, by such small numbers, that I'm not confident to say that is the winning. But I like so much my caterpillar. This will be my conjectures. That's the 4-2. That's my conjecture. I could be totally wrong. But then from there, you suspect that I will think of my caterpillar in all cases, right? That's the leads to natural, simple conjecture. And I'll stop here. I think, oh, no, wait. The important piece is here. There. Grazie mille.
Okay, thanks a lot for the nice talk. Questions?
Two comma three. Yeah, 2,3. Yes. We have not. So this is a. I mean, I'm already happy to have this. But yes, that's the next step. We've done the 3-1, and we got again the relo shape. Oh, guess no. Well, I would be tempted to guess to do two of them. No guess. Sorry, no guess. Too dangerous. But other people can guess.
I'm not going to guess. You mentioned in the non-local case the issue that the bubbles all align.
Yes.
Does that happen at higher or lower energy than crystallization?
I don't think we've compared with the energy of crystallization, so I would not know. But this is literally, so it could be that it's a local minima, but that is where the numerics went to. So it depends.
Do the numerics go to the lattice before it aligns, or do they align first?
No, first the lattice, then the align.
Ah.
That's why I think it's a second order, next
Yeah.
order, and
So
that's why it's so difficult. We tried to get some angles and see,
Okay.
but this was too difficult.
Thank you.
Some other questions?
Your closure theorem, why is not true for more than two improper chambers?
Yes, no. This is very much using the fact that it is too improper. It's very, very dependent.
But a guess on more than two?
I like my guesses when I have some numerics to back me up. Right now, I will not guess. That's too dangerous.
Thanks.
You have the periodic example with two improper phases, and with the improper phases, I've been wondering, because you have infinite area or volume, how do you enforce this in the periodic kind of model?
We are enforcing the literally the area to be so we are finite area, and then volume minus that is what we are enforcing as a strict constraint. Yes. But we're using periodicity though, right? So that when you calculate the perimeter, it's just a perimeter of what's separating the infinite region, right? So the periodicity is used, but yes, it's not infinite volume. There's no way.
Okay. Our questions or comments? Okay, so if not, we thank Leah again. So we continue with the Second talk of this morning, and Riccardo Scala from the University of Siena will talk about some results on relaxation of polyconvex functions with linear growth.
Thank you very much, Matteo. Let me thank also the organizers for the invitation. So, as the title says, I will talk about some results which have been obtained in the recent years in collaboration with many persons, starting from Giovanni Bellettini and somebody else like Ale Eshorbaghi, who was a student of Giovanni, and Simone Carano, another student of Giovanni, and somebody else, which I will mention during the presentation. So the problem I'm going to speak about is studying the relaxation of this kind of functionals, where u is a function, a vector-valued function, and the integral I'm going to investigate is the integral of a small f of the gradient of u. And we will consider this kind of functional where small f is polyconvex. I will say in a while what is the definition of polyconvexity, even if the most of you probably already knows these definitions. It was introduced by Ball in 1976, and although it has many applications in linear elasticity, we will focus on the case of linear or sublinear growth of these functionals. And this means that, let's say, that the prototype example of this kind of functional is the area functional. That is the functional which measures the area of the graph of a function u. So in the case that the domain omega is two-dimensional and the target space is two-dimensional as well, the functional will take this form. So we integrate over the domain the square root of 1 plus the square of the modulus of the gradient of u plus the Jacobian determinant of u squared. So, what is polyconvexity? Polyconvexity means that the function f of nabla u is, can be written as a convex function g of m of nabla u, where m of nabla u is the vector who contains all the determinant of the square submatrices of the gradient of u. So, for instance, if u is a map, as in the previous example, from R2 to R2, m of gradient of u is 1, which is, for convention, the determinant of the submatrix with 0 dimension, let's say. Then the determinant of the submatrices with 1 dimension, so 1 times 1 submatrices is all the components of the gradient. And then we have the determinant, which is the determinant, the 2 times 2 submatrix of gradient of u. So in this case, the area functional is exactly the integral of the norm, the vector norm of this m of gradient of u. So this is the prototype example. And then we consider linear growth in this sense, that we assume that the function g is greater or equal than a constant time the norm of the matrix m of nabla u, and we will also sometimes assume that it is also bounded above by some upper bound with linear growth. Actually, to be precise, we will not use both these inequalities always. So sometimes the first one is needed, sometimes the second one, but anyway, in this talk we assume both. And let me remark that this is a very different setting in contrast with the p growth condition, where p is greater than 1. In this case, it is assumed that g of m of nabla u is greater than a constant times the gradient, the norm of m of nabla u to the P. And in this case, the setting, the situation is completely different because actually the functional we are considering, this one, will be lower semi-continuous, and many good properties of this functional will be obtained easily. With linear growth, it is not lower semi-continuous. Actually, it is neither well-defined, for instance, for function of bounded variation. So we need a procedure of relaxation. This is standard procedure. We consider, so for a map, let's say, in a domain Rn to Rm, we consider the L1 relaxation of this functional, which is, for a function u, a general function in L1, we can consider the infimum between all the possible lim-inf of the energy of Vk, where Vk is a sequence of class C1, which are converging to U in the L1 topology. And this gives rise to a lower semi-continuous functional defined on L1, which actually can be also plus infinity on some L1 functions. Okay, we will denote by A the relaxed area functional, so the case in which F is the area functional. And we now collect some properties of this relaxation. Actually, thanks to this result of Acerbi and Dalmaso in 1994, we have that this relaxation extends the functional we started from. So for C1 function, the relaxed functional coincided with the one we gave at the beginning, and it is lower semi-continuous with respect to L1 topology. Moreover, the domain, so the space of function where it is the value of the relaxed functional is finite, is a subset of BV. Actually, it is a strictly contained subset. That means that there are functions in BV for which the relaxed area, for instance, is plus infinity. Moreover, so actually, let me say that a precise characterization of the domain is not available so far. So it's not clear what is the domain of this relaxed functional, even for the area 1. Then, moreover, there is this inequality. So the relaxed area is greater than or equal than the functional we started from, computed on M of nabla U, where nabla U is the approximate gradient of U, plus C0, which is constant. It actually coincides with the recession functions related to G, and the total variation of the singular part of the gradient of U. And often this inequality is strict. What I mean with often, I mean actually almost always, because there are only few examples in which this functional coincide with exactly these expressions. For instance, for C1, no, neither, yes, for C1 maps, okay, we don't have the singular part. For piecewise constant maps, we have something like this, but we have to avoid the triple junction between the phases of these functions. So we have only interface, precise interface between every phases. And yes, essentially these are the only examples in which we have equality. The last property, which is related to the third one, is that the functional f, the relaxed one, is non-local, in the sense that it is neither subadditive if we consider it on as a function of set. So we fix a function u over line u on a domain, let's say BR, a ball or radius R. And then we find that if we compute the same relaxed functional on different domains, for instance, on a smaller ball and on an annulus, we found out that even if the union of this small ball and this annulus contain the domain we started from, we don't have subadditivity of this. We don't have the subadditivity of the functional computed on these sets, but we have the opposite inequality, the strict inequality. The example, at least for the area functional, but it is easy to see that it must be true also for general functionals. And this was a conjecture by De Giorgi, and it was proved actually in the paper of Acerbi and Dalmaso. And let me say that it was conjecture only for the area functional, and De Giorgi suggested the functions, the examples to work with to construct the counterexample. He suggested the function, the vortex map, we call it the vortex map, that is exactly the function. I will write it here because it will be used in the next slides. X over modulus of x, let's say from a domain of R2 to R2, of course, actually to S1, because this is valued in S1. And the triple junction function, which we denote by UT, which is a function defined on a ball divided in 3 equal sectors with 120 degrees here. And the value, so this is the domain. The value it takes is alpha here, beta here, gamma here, which are the vertices of an equilateral triangle in R2. So this side we will denote the length by L, beta, and gamma. So this is piecewise constant functions, but also for these piecewise constant functions, we have this strange phenomenon of non-subadditivity of the energy. So a natural question is, okay, if we relax with respect to L1 topology, it becomes a mess. So we have non-local phenomena and this kind of difficult thing to deal with. But what if we relax in a stronger topology? So for instance, we found out that the domain is contained in BV. So we can also say, okay, let's relax with respect to the strict topology in BV. So this means we consider another relaxation, and we consider, as before, sequences of function of class C1, but which are converging to U strictly in BV. So strong in L1, and the total variation of the function we require that is converging to the total variation of the limit function. In this case, the situation is completely different, and we will see what happened next. So now, this was the introduction. I will focus a little bit on the area functional and review some results we obtained in the recent years. Then I will discuss more in detail the case of the relaxation with a strict topology, and then I will say something on remarks and open problems. So the area functional, of course, this is related to the plateau problem in maybe in codimension greater than 1. So I put this picture of a plateau problem in codimension 1 because I didn't find any picture for the higher codimension. Okay, so the tool I will use, but not in details, but I will use for this presentation, is the concept of Cartesian current. What is this? Okay, in this talk, we will define a Cartesian current in a simple way. This is, okay, we consider a function of class C1, and let's say from a subdomain of R2 to R2, And we will look at the graph of this function as a Cartesian, as a current, integral current, with no boundary actually, because this is a surface in R4. The surface is more precisely, so the graph of U is a subset of the domain times the target space. So this is contained in R4. And it is a manifold with no boundary. It can be treated as integral current. And so we now assume that we are approaching a function U in L1. So these VK are converging to U in L1. And let's treat the area functional. So let's assume that the total area of the graph of VK is uniformly bounded by a constant. This is a natural question, a natural assumption, because we are considering the relaxed area functional. So if the relaxed area functional of the function U is finite, we are forcing to assume this. That actually there existed a sequence VK of class C1 which are converging to U in L1, for which the area of the graph converge exactly to the relaxed area of the function U. This is by definition the relaxation of the area. So this is in general finite, and the graph of VK, so they are integral currents with uniform bounded area. They are converging in the sense of current to something. So what is this something? It is something that should contain the graph of the limiting function, but can contain also something else, which is called the vertical part. Now, what is this vertical part? In general, it is not known how this vertical part is, and it is neither unique. But the only thing is clear is that since the currents on the left here, the graph of VK, are boundaryless, also the current, the limit 1 is boundaryless. And so the boundary of the graph of U must coincide with minus the boundary of the vertical part. So if U is singular, for instance, a BV function with a jump somewhere, this vertical part has to connect the two traces of the function from the left and from the right of the jump, in some sense. This is clear if we look at the situation in codimension 1. So for instance, let's consider here in a one-dimensional domain a scalar function, which is the red, whose graph is the red one. We approximate it with a C1 function, which is the blue one. At the limit, what we get? We get something that coincides with the red graph, but has to connect in a vertical way the two limits on the left and the right of a jump of the function U. This is so the limit in this case is unique. Then the integral currents we obtain at the limit is exactly the integration of this graph, which has vertical lines, vertical segments. This is the generalized graph of the function U. The same holds if we are in 2 dimensions, but for scalar function. So we have, for instance, a function which jumps on this segment. At the limit, we get a current which has exactly which is exactly the integration of the graph of U on the left and on the right, but on the jump set we have a vertical wall connecting the two graphs. In codimension 2, it is more complicated because if, for instance, we have a domain here, a 2-dimensional domain, and we have a jump on this segment. So we have U plus here, U minus here, and this is for instance, valued in R2. Then we expect something which has to connect U plus to U minus, but it has to connect the two values of the functions on a segment, which, if we look it in omega times R2, which is the space where the graph lives, this object connecting the two lives on this segment, which we call S, let's say, times R2. But now S is one-dimensional. R2 is two-dimensional, so this is a three-dimensional space. So we have to construct a surface which is not constrained to be in a two-dimensional set, but in a three-dimensional one. So we have more space to construct this. And this is the main reason, because in the end, we don't have uniqueness of the limit of the integral currents. So the first example is given by the triple junction function. So Acerbi and Dalmaso used it to construct the counterexample of the subadditivity of the area functional in codimension 2. And later, Paolini and Maurizio Paolini and Giovanni Bellettini proved a more precise upper bound. They proved that the area functional computed on the triple junction function is less than or equal than the area of the graph, which coincides in this case with the area of the domain, because the function is piecewise constant, plus 3 times the area of a minimal surface in R3, which I'm going to discuss in a while what it is. And actually, this 3 times this area correspond to 3 times a minimal surface that we have to put upon this side, another one equal upon this side, and another one equal upon this last radius, in order to fill the holes of the graph of U. So this is the limit of the graphs of an approximating sequence converging to U. How are A mean computed? They are minimal surfaces which correspond to this plateau type problem. They construct a domain R smaller L, which is a rectangle here in the plane ST, and they consider a parametric plateau problem, which is they minimize the area functional in codimension 1 of a function of class, let's say, W11, such that they are fixed at the boundary, and this phi, which is the boundary value, has a graph exactly this red graph. Okay, so I will not be more precise, because I have a picture which describes the graph of phi. And on this side, where we don't have the graph of phi, the functions are free to do what they want. We minimize this object. They proved that the minimizer is minimal surface, yes, a minimal graph which is of class W11, whose area is exactly this contribution. So what they conjectured was that this contribution, and more precisely, this minimal surface is the right object to put upon this true radius in order to get the minimal, the limit of a minimal graph. Sorry, of a recovery sequence for the area function. So if Vk are converging to some GU plus a vertical part, this vertical part of UT, which is the triple junction function, is exactly 3 times this object. A similar phenomenon is seen in this case of the vortex function. We have that if we compute the relaxed area functional in a ball centered at the origin of radius r, the contribution is exactly the area of the graph of UV, which is the vortex map, plus a singular contribution, which is the area of CR, which is another minimal surface obtained by a similar plateau type problem. This problem I I didn't explain here, I didn't write all the condition we have on this, but I can summarize it. Do I have some eraser? No. Sorry? Ah. Okay, thank you. So we minimize, we take a rectangle or radius, no, sorry, or dimension here 2 and here 2r, where r is the radius of the domain, br. And we consider a graph of a function h. You can assume it is convex, but in general, it is whatever, a measurable function. And we consider the minimum of 1 plus gradient of psi squared, so the area of a graph of a function psi, whose domain is exactly the subgraph of this function h. And we fix some boundary condition on this domain, which are here, the boundary condition is a semicircle, so as in the picture here. Here another semicircle. Here is 0, and on this graph is 0. So we minimize on the area of all functions with this constraint. Actually, h is free, so we minimize also on the shape of h. And what we get is that the minimizer is, if the radius r is small, we get a sort of half a catenoid. So the shape of this minimal surface will be a graph of something which has it's exactly half a catenoid. Okay, I'm not very good in drawing this object, but you can imagine that if you symmetrize, you take the same object and you symmetrize it with respect to the domain. So you put the same object on the opposite side of the blackboard, you got exactly this catenoid, which is not a classical catenoid because it is constrained to contain this vertical segment, which correspond to this edge of the rectangle. And if instead R is big, as in the catenoid case, you get that the minimizer is singular and correspond to the area of two circles or radius 1, which correspond to the doubling of this boundary value. So, some observation. In order, if R is small, we have that the area of this catenoid, actually we have to take half the area of the catenoid. Anyway, it is smaller than 2 pi r. Why 2 pi r? Because 2 pi r is exactly the area of a cylinder. We take a competitor for this problem. As a competitor, we take the function h, exactly the constant 1, the constant function, yes, because this corresponds to 1 and this to minus 1. So the constant 1, h equal 1. We have here this boundary value. We take as a competitor exactly the function which is constant in this direction. So whose shape is exactly half a cylinder. This has area 2 pi r. And at the same time, so we say that if r is big, the area is exactly pi. So with this remark, we can prove the conjecture of de Giorgi, which actually was already proved by Acerbi and Dalmaso with estimates. But now we have some more precise description of the singularities of this object. Now, how can you prove this? We prove this because if R is big, so the radius of the domain, the capital R is big, we have that the area of the triple junction function, no, sorry, the vortex map, is exactly the area of the graph plus pi, because pi was the singular contribution. On the other hand, if we consider R2 small, we see that the area of the graph of U, or generalized graph of UV on BR2 is smaller than the area of the graph on this domain plus 2 pi R2. On the other hand, if we consider an annulus, whatever it is, on the annulus, the function is regular. It's infinity. So the area of the graph coincides with the functional we start from, which is exactly the classical area of the graph. If we sum these two, and R1 is close to R2, these two contributions are very close, and their sum is almost a little bit more than this. But the singular contribution, here we can do it very, very small. And here we have pi, which is much bigger. And so we get this inequality. This is the proof of the conjecture. And now I will resume in a while some more general results. That is, okay, we consider a very special class, a very special function, which is the vortex map. It's a function with value in S1. We can consider general Sobolev function with value in S1. We know from the results of Bresi and co-authors that the Jacobian determinant, the weak Jacobian determinant of this is a sum of dipoles weighted with pi. And we can introduce the flat norm of this object, which is the supremum between the duality product of lambda and phi, which phi is a Lipschitz function, which is in L infinity smaller than 1, and whose gradient also is smaller than 1. And our result is that the area functional, the L1 area functional, is always smaller than the area of the graph plus the flat norm, a constant, let's say, okay, times the flat norm of this. And this is not a precise, this is not sharp, okay. Anyway, also for piecewise constant maps, something similar can be done. If you have a piecewise constant map which takes 3 values, as in the triple junction example, we have that we can give a notion of a weak Jacobian determinant of the map. And also in this case, it happens that the Jacobian determinant is a constant times a sum of dipoles, where these dipoles are, these Dirac deltas are exactly concentrated in the triple junction of these maps. We can have also quadruple junction and more, but we get always a Dirac delta there with the same, more maybe a multiple of this constant. Okay, and the result is similar. We have that the area functional is more than the area of the graph plus the singular part of the graph. I forgot here the area of the graph, which actually coincides with the area of the domain omega, plus C times the flat norm of U. Okay, this is a generalization, but always this is not sharp. We don't know anything else about this relaxation. Okay, let's see what happens if we relax with the strict convergence. So actually, I spoiled that all this non-local property will disappear, at least if the domain is two-dimensional. If the domain is three-dimensional, this is not true. But okay, so let's assume that omega is two-dimensional. We consider, for instance, the area, the relaxation of the area with the strict convergence in BV. And now Mucci proved a couple of years ago that the limit, in this case, of the as currents of the graph of a sequence VK converging to U strictly in BV is uniquely determined. So also the vertical part of the graph of the current, of the Cartesian current, is unique. So in this case, maybe there is more hope to find a precise value for the relaxation. However, it is still true that this inequality holds, and this is because this vertical part could also disappear, and we can at the same time have some singular contribution for the area, but we will see it maybe later. Anyway, this is not true for S1 valued map. So we obtain with this student of Giovanni that if U is W11 with value in S1, then the relaxed area in the strict topology is exactly the area of the graph plus the total variation of the Jacobian determinant of U. So we have a precise expression for the area functional. We have also a precise expression in more general situations. So for instance, let's take a zero homogeneous map. So we consider a variant of the vortex map where we compose the vortex map with a phi, where phi is any curve between S1 to R2, also singular, with a self-intersection, with so not necessarily injective. The result is that the relaxation of the area in the strict topology is equal to the graph of U, the area of the graph, plus a singular contribution P of phi, which is obtained as a singular protoproblem. Exactly, this is the two-dimensional protoproblem, where as boundary value we have the curve obtained as the image by phi of S1. This can be, for instance, if we have a vortex with high multiplicity. So in this case, phi is something running around the origin more than one time. We will have that the plateau problem is solved by the infimum of this object is exactly k times the area of the circle, where k is the multiplicity of is the degree, let's say, of the function around the origin. And also we have some other results. So if U is a BV function jumping on a curve, then the relaxation of the area, if the traces of U are good enough, let's say, the relaxation of the area is the total variation, the area of the graph, plus this object, which is exactly this corresponds, okay, X affine is an interpolation between the two traces, a linear interpolation between U plus and U minus, and we take the area of this object. Okay, in any case, there is an integral expression for the relaxed area function. This is a general result, actually, and we found out this, that in the case of strict convergence, also for the function f, so whatever is the polyconvex function we start from, we have that if we consider the function, we fix U in BV, and we consider the function of set which send a set A subset of omega to the relaxed functional computed on A, then this is the restriction of a Borel measure. This was not true in the case of relaxation L1. So if this is true, probably there exists an integral representation for these functionals. We have example for the area here. We don't know how it is in the general case, but anyway, we know that it is a measure. And so now, in the last 5 minutes, I will not inspect the proof, but I will only say that it is based on the Giorgi-Letta theorem, which actually corresponds to check that this set function is non-decreasing and superadditive. It is also irregular in the sense that if we take an open set A, we can compute the relaxed functional f as the supremum of it computed on sets B, open sets B, which are compactly contained in A. And then finally, it is finitely subadditive. So we have to check this stuff. And let me only mention that in contrast with the L1 relaxation, in which, for instance, the non-decreasing of this functional is obvious, In this case, it's not, because what is the idea? Let's consider the L1 relaxation. So we have a function u defined on a domain omega. We have a sequence of function vk which are converging to and such that the relaxed area, the relaxed functional in general of vk on omega are converging. No, sorry, we can take vk in C1, so we can also put the starting energy. They coincide actually. If this converge to u of omega, so we call it a recovery sequence, we have that vk, okay, we have that if we restrict the domain, we take a domain A inside omega, then the same recovery sequence is converging in L1 on this subdomain. And so in general, we have that f of vk in A converge to something, let's say, that is at the limit greater or equal than f of u in A. Greater or equal because nothing can assure me that vk is a recovery sequence for this domain. Actually, in general, it's not true. But anyway, we have that this is less or equal than this is less or equal than this, and this converts to this. So we have non-decreasing property of the function of the relaxed functional f. This is not true in general. No, this is true, but it is not easy to see in general because if now we consider the strict convergence, we do the same reasoning and we say, okay, now this is still true, but nothing can assure me that vk is converging to strictly in A. Because if I restrict to subdomain, we don't inherit in general the strict convergence. So we have to modify this in order to get strict convergence and in order to still obtain this inequality. Okay. No, sorry, the inequality, the important inequality to compare this with this is this one. Okay. So it is not trivial, but anyway, this is a work done by cut and paste arguments, let's say, for recovery sequences. And the crucial lemma is this one. So if we have a subdomain of omega which has a C3, at least a C3 regularity, whose boundary is C3, then a recovery sequence for f on omega for almost every t is also a recovery sequence in AT, where AT is this set. So the points in A whose distance from the boundary are greater than t. One can prove this, and then, okay, this is the crucial step. Then the proof goes on with cut and paste arguments. Okay, I don't want to bother you more on this. Let me say some remarks and questions, which are open. So we, at the beginning, I said, okay, we need this inequality. Actually, this is not really needed for the relaxation in the strict BV topology, because we can apply, for instance, the same results to the total variation function. This is called total variation, but actually it computes the total variation of the Jacobian determinant of U. Then also, let me say that the target space, we say in the talk, it has dimension 2. Actually, could have also dimension m greater than 2. But it is crucial that the domain is R2 is in R2, so it's two-dimensional. This is because there is a counterexample due to Karan and Much in 2024, so last year, proving that if we take omega, for instance, a sphere in R3, we consider the vortex map x over modulus of x, then they could prove that the area functional relaxed with the BV topology, the strict BV topology, is still non-local. And this is essentially due to the fact that if you have a strict convergence in a two-dimensional space, then if we go on a line or on a curve, the strict convergence is inherited, almost every curve, let's say. And this has as a consequence that we cannot concentrate so much gradient on curves, because we cannot, for a recovery sequence, we cannot create concentration of gradient on curves because we have strict convergence to the limit 1. This is still true in 3 dimension because we have that in surfaces we cannot concentrate so much gradient, but we can do it on curves. And so actually they are able to prove that recovery sequence concentrate on lines in R3. So two codimensional object. Okay, the last remarks is that we don't know exactly what is the integral representation of this relaxation. It is not so simple because we have this inequality which could happen very often. An example of this is if we take this function, which is zero homogeneous, like the ones I introduced some slides ago. So we consider this function called U8 as phi 8 of x over modulus of x. And what is phi 8? Phi 8 is a curve. So it's defined on S1 with value in R3, in R2. It's a curve which do this, that's this strip. Start from the origin, it does this, it runs this circle in clockwise order, run this circle in counterclockwise order, and then he do the opposite. So he start with the first circle in counterclockwise order and then run the second circle in the opposite order of the first trip. For this curve, since we are running the same object with 2 opposite directions, we see that as a current, this is 0, this is null. And you can prove that the graph of this U8 as a current is boundaryless. So the boundary is 0, because actually, in general, for this kind of map, you have that the boundary is exactly a Dirac delta in the origin times the push forward by this curve of the integration, standard integration over S1. Can prove this. So if this is 0, this is 0. So this is, let's say, a Cartesian current in the sense that it is boundaryless as a graph. At the same time, if you consider the relaxed area function, you get, as in the previous result, that you pay the plateau problem as a singular contribution related to this function. And the plateau problem for this map, even if it is 0 as a current, is not trivial. It's 2 times the area of a minimizing circle filling this object, this curve, is 2 times 1 circumference. So we have a singular contribution and you have this inequality. So this is to say that in general, it is not clear, it is not strongly related, the area of the relaxed functional with the Cartesian current you get at the limit. Okay, with this I finish and thank you for the attention.
Do you have some hopes to get a strict convergence of minimizing sequences? I mean, to make this relaxation.
Sorry, you mean in the L1?
No, the strict. So you relax with respect to the strict convergence. In
Yes.
LG, but you should relax with respect to a topology with respect to which minimizing sequences are compact. Because you want to look at the behavior of minimizing sequences in the end when you look at the relaxation. So
you have always compactness in the sense of currents. Okay. So for minimizing sequences, for sure you have that the currents related to the graphs of these minimizing sequences is okay. So probably the question is more related on the on a plateau type problem.
yeah, no, I mean you relax with respect to a topology which is a strict convergence in BV.
Yes.
Okay. But does it give you, so you get results, so integral representation of the relaxation. And my question is, does this result give you some informations on the asymptotic or on the convergence of minimizing sequence? So when you start with a problem with a minimization problem with boundary condition, whatever you want, you want to get compactness on your minimizing sequence.
Yes, okay, I understand.
So in L1 you get it easily. But the strict convergence in BV, do you have?
Not exactly, no, because for instance, just to say something, if you consider a non-parametric plateau problem, so you fix some boundary condition on the boundary of a domain, you want to find a minimizer for the area. This is not true in general that the minimizer converges strictly, because you can have non-local phenomena inside. Let's say if you fix a boundary condition, you avoid all the non-local phenomena involving the boundary. So in the stupid example of the vortex map, if you relax the area in L1 topology, you get that the limiting current is something concentrated on a radius connecting the boundary. If you want to, for instance, study the plateau problem codimension 2 in a parametric, in non-parametric case, so you fix the boundary which is x over modulus of x, you avoid this bridge, because yes, the recovery sequence cannot do what the recovery for the L1 topology does. But anyway, in this case, probably you get also strictly, I don't know, but if you have a dipole here, you have interaction between these two poles. Also, yes, for minimizing sequence, I think you get interaction. Also, if you fix the boundary. So, no, I don't have much hope for this.
Okay. Other questions?
Forse Roberto.
For the triple junction function, for the plateau problem, the free boundary is planar?
The free boundary, okay, let me say, no, in that case, what do you mean with planar?
You described the plateau problem for
yes,
the...
Yes.
And
okay.
then...
No, the plateau problem in that case is, okay, we have a rectangle, okay, in this plane. Then you have here a third dimension. You fix as a boundary for a scalar function here. 0 on this side, on this edge, 0 on this edge. This here is not 0. The graph of the function is something like this. Here is free, but it's free not to stay, not as in the catenoid case that you have some curve in the domain in the domain of phi, which is the minimal surface you want to get, is constrained to be up this above this curve. This is the domain is the whole rectangle, and you have free trace on this edge. Okay, sorry, I forgot to mention that these kind of problems are used to construct this vertical part of the currents, and can be generalized. Actually, we made a work with Roberta, where we generalize this non-standard plateau problem with partial free boundary. But yes, exactly this, in this case, you have a free trace on this, so it does not is not really related with that problem we studied.
Other questions?
So for this three-dimensional case in which, if I understood correctly, you don't have subadditivity, right?
No.
The 3D. Do you have a guess for, I don't know, topology?
The topology, yes. No, I don't have a guess, but I would say that somehow you should require that since you are in 3 dimension, let's say the parallel with the 2 dimension is that if you are in 2 dimension, you require that the 1 times 1 minors of m of gradient of u converge strictly to, because this is exactly the gradient, converge strictly to the total variation of the limiting function. So somehow, if your limit function is Sobolev, you could require that the 2 times 2 minors of your m of gradient of u in the 3-dimensional case converge with the total variation to the 2 times 2 minors of the limiting function. But you cannot do this for BV function because you have to introduce a notion of 2 times 2 minors. Somehow it is possible, but it's more complicated. So I think you have to require strict convergence, not of the gradient, but of the 2 times 2 minors. This is my hypothesis.
Thanks.
So we can start with the last talk of this morning, and will be by Theresa Simon from the University of Münster, and she will talk about linear stability of the self-similarly shrinking lens.
Well, welcome to the talk. Thank you to the organizers for inviting me here. It's always a pleasure to be in Pisa, and thank you to Matteo for the kind introduction. I'm going to talk. In fact, this is my first talk about solo work on mean curvature flow, so I'm a bit nervous. I can't hide behind Tim Lokes and Julian Fischer anymore. So I'm going to talk about mean curvature flow in its network form, in a sense. So I'm going to work with the network gamma, and I'm going to say that this evolves by mean curvature flow if along the curves the normal velocity is given by the curvature of the curve, and the signs are chosen in such a way that convex regions shrink. And also I need conditions at the triple junctions, and there I assume that these are all 120-degree angles. That's your Herring angle condition that you already saw that in Leah's talk in the beginning. And just, I said convex regions shrink. That tells you right away that, well, you expect singularities in these flows, and I'm going to be interested in stability of certain types of singularities. So before I show you the singularities, let me show you, in fact, how I'm going to phrase stability in this case. So for a point in R2 and some time t0 bigger than 2, let me define the Gaussian if I would put a time dependence here. Some of you will recognize this if I put the time dependence here and divide by the time here. That's essentially the backwards Gaussian. And which appears in Huysken's monotonicity formula, and I'm going to be concerned with functionals f depending on x0 and t0 being essentially the weighted interface length, where the weight is given by this Gaussian. Now, so this is already what this f functional already appeared in Huysken's work in 90, and then I believe this is the next definition is due to Mantegazza and Magni. In 2009, you then define the entropy of gamma as the supremum over all locations and all times of the f's. And there is a nice property of this, namely that if you plug in a network that evolves by mean curvature, then this entropy is decreasing in time. And that, again, this here follows by Huysken's monotonicity form. So say for some reason you know that a network is a local minimizer of lambda, then if you start near to this network, you would expect to stay near to this network. And I'm going to use these in the case of some very special solutions to mean curvature flow, namely solutions which are given where the mean curvature flow is given by dilations. Again, by Huysken's monotonicity formula, you can prove that such flows arise as parabolic blow-up limits when you run into a singularity, or at least certain types of singularities, and I'm going to ask whether those are stable. And so I'm going to call gamma a self-similar shrinker. If, well, okay, I have a network, I have Herring's angle condition, and the curvature is given by minus gamma, so my individual curves I call gamma. Gamma prime divided by 2, I think. Correct. Normal component. And where by perp I denote the counterclockwise rotation by 90 degrees. If you want in complex notation, you multiply by I. It's one of the nice properties of these is that, so, okay, this does not depend on time now. So what I'm really doing is I'm taking such a mean curvature flow I'm taking a network whose mean curvature flow is given by dilations. I fix a specific time slice, and then, this tells you that this encodes velocity being normal velocity, being that coming from dilations, and then curvature equal that is the mean curvature flow equation for a specific time. If you let it evolve, this will shrink self-similarly. Now, I'm also okay. So now, nice thing is you can characterize these solutions in terms of the Fs, namely gamma is a self-similar shrinker. If and only if gamma is a critical point. Of, well, 0 and location 0 time 1. If you want, that's my choice. The fact that I didn't subtract something from gamma, and the fact that I chose this prefactor 1/2 in combination with the with this version of the Gaussian. So, okay, we know a self-similar shrinker is a critical point of my F01. I know that up to translations and essentially dilations, this thing is decreased in time. So you ask yourself, well, is gamma not only a critical point of F01, but is it actually stable with at least up to translations and dilations? Because those will turn out to actually be in unstable modes. But right. So that's the basic question. Is which networks are linearly stable with respect to F01 and up to translations and dilations. And at this point, I should give you some examples for self-similar shrinkers. I'm going to start with some rather, if you want, boring ones. Any line, straight line through the origin in R2. I should have said that. I'm in R2. I'm a two-dimensional mathematician. So any straight line through the origin is a self-similar shrinker. The triple junction is a self-similar shrinker with the triple junction being in the origin. Okay, you have a certain circle is a self-similar shrinker if you choose the radius in the right way. Plug into this condition, figure out what the radius is. I'm not going to talk about the ball. And then you have more complicated things, and the next one is going to look familiar to you, although that's deceiving. there is something that is lens shaped, but this is not the shape that Leah was talking about, because these arcs are not circular. This gives you an ODE for the arcs, and well, if anybody knows an explicit an explicit solution or even semi-explicit solution to this, I would be interested. I don't even know if you can represent it in terms of special functions. So, okay, this is the lens I'm going to talk about later. There are a bunch more. I should also this one kind of showed up in Leah's talk, although the same caveat applies. You have a 3-ray star. And of course, you have 120 degrees everywhere, but again, the connecting arcs are not circular. So this would a 3-ray star. You have something which looks like this, which is called the Brachyspoon. And then you can get into more exotic objects. You can have a 4-ray star. You can even have a 5-ray star. Let me not draw that. You can guess how it looks like. It's like 5 rays and then circular arcs. So this is kind of, and then there are similar things as the Brachyspoon, just with more triple junctions. There is the fish, and there is the rocket. And well, as far as I'm aware, those are the only self-similar shrinkers with one enclosed region. You may also get self-similar shrinkers with more enclosed regions, but those are known to be unstable, so I don't care about them in terms of stability. Now let me see. The fact that the line is stable should not be too surprising, however you prove it. The triple junction should also be stable. The fact that the circle is stable is, I think, first due to Epstein and Weinstein. In 87. Alessandra proved that the Brachyspoon is stable in a certain sense in 2016. And for the lens, there are works by Azuni et al. It's a whole bunch of people. I don't know. I don't remember them all. And then there's Billet in the same year. There's Benettini and Matteo. I put those in brackets because they had to assume that your perturbations, the thing you started with, already has some symmetry. And so that's what I know regarding stability. And then for this whole family of things, somewhat recently, Cheng proved that these are all unstable. Are all linearly unstable. Even if you remember to take care of translations and dilations. And so what I'm going to want to show you today is that I can do linear stability for this guy. But let me. So I'm building somewhat on the work of Cheng, and also on work of Kolding and Minicozzi. So I they computed the second variation for me. Also, the eigenvalue problem I will give you in a second. So this is Kolding and Minicozzi. In 2012 and Cheng in 21. They did it for surfaces, Cheng did it for the network case, but the formula is really quite similar. And the second variation, I'm not going to write it down in complete detail because you will see. So my second variation lives on normal variations. And it takes the following form. So I integrate over my shrinker, and then I get v prime squared minus curvature squared plus 1/2 times v squared d multiply with the weight and integrate. And then there are triple junction terms. I'm not going to write them down because they are a bit of a pain notation-wise, and I'm going to only work with the eigenvalue problem in a second anyway. But you see, you have one term where stability has to come from. That's the derivative. You have the lower order term potentially giving you, being a source of unstableness, and the triple junction terms are also don't necessarily have a sign. So, this is what we work with. And where? Yes. Yes. So v, if you want, v is a function. I'm okay. So I'm going to let me skip ahead a bit and with my talk, and doing that, I will answer your question. So let me go with the lens because then things are easier. So the lens, I'm going to say that the triple junction on the right is at p, 0. On the left, it's at minus p, 0. And I orient the curves like this. Gamma 1, gamma 2, gamma 3, gamma 4. These are the normals. This is N2. And now the gamma 3 and gamma 4 are maps from some interval. I should make this closed. Into R2 with the obvious symmetry. And now V is a tuple V1, V2, V3, V4, where V1 and V2 are maps from P0 into R, V3, 4, and these are maps from minus L into R. So, I have domains on which these curves are parametrized, and which the curves of the shrinker are parametrized, and then the variations are parametrized on the same domains. But yeah, those are if you want to get back to an actual physical variation, you would need to construct variations which have these functions as in their normal components. Then you have, of course, at the triple junctions, because you need your perturbed your perturbed network to also have 120-degree angles. You need the Herring angle condition. So at P 0, the Herring angle condition for the unperturbed thing is minus n1 plus n3 plus n4 equals 0. At minus p 0, you have just the sums. I mean, you can see that in the picture. I mean, here at this triple junction, they look like they, go round once, and n1 is flipped with respect to n2. So these are the two. And now the compatibility conditions, so the linearized Haring angle conditions are, precisely what you get from here. So minus v1 plus v3 plus v4 equals 0 at p 0, and then v2 plus v3 plus v4 equals 0 at minus p 0. So this is, if you want to do it for more general networks, you have to put all of that, write all of this down and put it in there. But does that answer your question? Cool. Okay, and I left some space here. The theorem I want to prove, or show you a sketch of the proof, is the following. It's not on the archive yet. I have the proof of this. I still want to do a bunch of generalizations, which are almost done, but I hope to have this on the archive very soon. As Leah put it, I'm taking a risk. The theorem is that the lens is linearly stable, is a linearly stable critical point of f01 up to up to dilations and translations. Okay, this is how I parameterize the lens. Now I have a second variation that gives me an eigenvalue problem. Let me give you the eigenvalue problem. Other questions? I'm going to prove that the eigenvalues that come from this operator are all strictly positive up to those that you expect. Those that you expect to be negative. So, second variation means you have your energy landscape. You have your functional f01. You have a critical point, so that it's the tangent plane is flat, and up to some control directions, what I'm going to prove is that the second variation curves up. And in that, if you think of finite dimensions, you can prove that if your second, if you have a critical point, if your second variation, so your second derivative is strictly positive, definite, then you have a local, then your critical point must be a local minimizer. I'm not going to prove that. I'm only going to talk about the second derivative part being positive, but that's the background. Sure. Right. V is in H1 of the lens with respect to, it's essentially in this space. So it might actually go to infinity. It just goes to infinity slower than the Gaussian. Okay. Wrong here. Now, eigenvalue problem. This now, again, Cheng did me the favor of computing this before me. So on the individual arcs, I have v minus v prime prime plus 1/2 gamma I dot gamma I prime vi prime minus curvature along the ith curve plus 1 squared plus 1/2 vi equal lambda vi. And this, so lambda is in R for some. And this is for all the curves, of course. I have the linearized Herring angle conditions. At the triple junctions. And then I have from the triple junction terms, and here is really where I want to put those down. I get the following conditions, so the following derivatives along the curve must agree at the triple junction. This is a 3, 4 squared, 4 prime. This is at minus P0, and at P0, you have the same, you just have V2 here. And then the rest is the same. So the goal now is to find the to solve this in sufficiently many situations. And let me show you how I'm going to do that. Let me remind you maybe that rho 0, 1 was 1 4 pi square root t, no. Here. Okay. Now, just from your, if you want invariances of the problem, you already get a bunch of eigenfunctions. And these are the following. So my F01 is not dilation invariant, but I really want to talk about the lambda entropy, which is dilation. In the end, I want to talk about, you would want to talk about the lambda entropy. That one is dilation invariant. So dilation gives you an eigenvalue, which I denote by Vd. That's just given by curvature on all the arcs. And the eigenvalue of that is -1. So dilations are unstable. Okay, but I set up to dilations anyway. Then you have translations. There you have translations in direction, W. Those are given by W dot the normal, where W is in R2, and maybe you should take out 0 because your eigenfunction shouldn't vanish. These all have eigenvalue -1/2. Again, unstable. Again, I took care of them in the formulation of my theorem, so that's fine. You see here, though, that in general, and in particular for the lens, you have eigenvalues with higher multiplicity. So even though we're talking about ODEs, you get multiplicity of eigenvalues, but because we're really talking about a coupled system of ODEs, is the point. So these are unstable. And then we have one more coming from rotations. Those I will denote by VR, and that's V gamma dot gamma prime, and the corresponding eigenvalue is 0. So that's all already in the literature, and what I'm going to have to do is to say that, well, these are the only eigenvalues, the only eigenfunctions and eigenvalues with eigenvalue less or equal than 0. So I do that. So it's what makes this problem tricky is that you look at this thing, you have 3 eigenvalues, you have unstable, multiplicity 1, multiplicity 2, multiplicity 1 again. So you're dealing with a 4-dimensional bad space. You might say, well, how on earth am I going? At best, maybe in the literature you find how to estimate lowest eigenvalues. We're going to have to estimate the 4th eigenvalue, but we can do it. And here is how. So one thing that's good to look at is at what just happens on the straight rays, right? Just look at the ODE that belongs to the straight ray, and let's see what we can say for that. So and again, I only care about lambda less or equal than 0. And on the line, the equation gets a little bit simpler. So curvature is 0. Gamma I dot gamma I prime, that's just T. Lambda prime. And what curvature is 0, U lambda equal lambda U lambda. And let's put growth conditions on this, and those that correspond to the Gaussian up there. If I have a non-trivial solution, those are for lambda less or equal than 0. These are non-vanishing everywhere. So the following operator is defined. If I map lambda into u lambda prime at p divided by u lambda of p, this is the Dirichlet to Neumann map. So this is well defined. And you can prove that it is non-increasing or strictly increasing. How do you do that? Well, you can solve these equations in terms of special functions. In terms of so-called parabolic cylinder functions. Similarly to, say, Bessel functions, those are non-explicit, but you know everything if you know where to look. Okay, so that means we understand reasonably well what happens on the rays. And now we Now we have to put that to use in order to deal with the whole thing. Let me first let me first talk about compactly supported V's. You might think those are the easier case. In a sense, they are, but you need to be more precise here. So if V is compactly supported, this tells you that V1 and V2 must vanish. So you're only left with the with V on the curved parts, and in order to deal with that, you use that on the curved parts, the curvature, which is the lowest eigenvalue, is strictly positive. So that allows me to say, well, let me divide the third component by the third component of the lowest eigenfunction, of the eigenfunction with the lowest eigenvalue, and it turns out that simplifies the ODE. Namely, the problem now looks like e to the gamma 3 squared fourth f prime prime equal lambda plus 1 e to the gamma 3 what is that f. And also the boundary terms do us the tremendous favor of just giving us Norman boundary data. This is a perfectly well-behaved Sturm-Liouville problem. If you don't know Sturm-Liouville theory, that's fine. Think of you know, your favorite second order ODE, where you know you just don't have the weights. Then you have minus second derivative equal lambda f. That's sine and cosine, and you see that in phase space those oscillate around the origin. You have the same thing here, and in particular you can prove that the nth so the nth eigenvalue so the eigenfunction of the nth eigenvalue, and here n is an n including 0. I order them by size, by increasing size. This has precisely n zeros on minus LL on the interior. So, okay. So VD, that's supposed to be my lowest eigenfunction. That gives me FD equal 1. This has no 0. The lowest eigenvalue, and it is the lowest eigenvalue with lambda d plus 1 equal lambda d plus. How did I messed this. This has no 0. So for lambda, I'm on the wrong page. That's what's confusing me. So this gives me the eigenvalue lambda d plus 1 equals 0. Then another one is translation along the lens. So that's VTE1. This gives me some function FTE1. This has precisely 1, 0. Namely where the arc is tangent to the translation. And that gives me lambda t plus 1 equal 1/2. And the other eigenfunctions are not complexly supported. So the next so what I need is I need to estimate I need an estimate for the third eigenvalue of this guy, and I need to prove that the eigenvalue is strictly bigger than 1. So and you know, there you need a number. You need an explicit number to do that. The way you get your hand on that is you compare it to the unweighted Poincaré inequality, and you know, use some rough numerical statements about the lens. So you need to know how long the arc is. You need to know how far you need to know, for example, how far is it away from the origin at the furthest and at the closest. Things, you know, harmless. In terms of numerics, that's harmless. You know, I'm not doing a hardcore computer assistive proof here. I just need a bunch of properties you could read off of some standard numerics. Okay. Now you might say, okay, the compactly supported are not, you know, are not super, you know. What about the, you know, what about the general ones? And for the general ones, somehow, so here the thing is that yes, your eigenproblem is very simple, but you need quantitative information. For general V, you can make do with qualitative information, and let me show you how. So for general V, so the lens has symmetry, right? We should exploit that at some point. If I flip V4 and V3, I still get an eigenfunction with the same eigenvalue. Okay, so I can define, you know, I can do, if you want, symmetric and antisymmetric variations. So these are so the first one is V1, V2, and then you symmetrize in the third and fourth component. And for the other one, you know, the first two are 0, so I don't care what you have out there. I already dealt with those. This is, you know, this is precisely compact. You know, these are compactly supported apparently. Now, okay, so I only have to deal with eigenfunctions that have this symmetry. So for V with V3 equal V4, now my geometric situation is nicer. And I have V1 here, I have V2 here, and I have V3 here, and I only put the, you know, the lower arc as dotted because, you know, by symmetry I don't have to deal with that. And here I have to deal with the full, you know, here I have an ODE, here I have an ODE, here I have an ODE, I have boundary values between them, and I have to consider the whole problem, the whole coupled problem, just with an arc less. And the idea here is, you know, so for classical Sturm-Liouville theory, I just told you that the nth eigenfunction has precisely n zeros. You could imagine that the same holds here. We already know that v2 and v1 are not going to have zeros by this non-vanishing property here. So I'm going to want to prove that the nth eigenvalue on the middle part has precisely n zeros. You can do that. And I'm probably running a bit out of time. Well, how do you do it? Well, again, you look in phase space. There, it oscillates around the there your solutions oscillate around the origin, and using shooting methods, you typically using shooting methods you can prove these statements. Here it's a bit different because you replace the left ray and the right ray you replace by the Dirichlet to Neumann maps, and then as opposed to shooting a stationary target from a stationary platform, you shoot a moving target from a moving platform, and you need to make sure that your monotonicities work out, but they do. But then again, you count zeros. So the translation with respect to E2, so moving the lens up, this has no zeros. That is in this symmetrized version. This is then the lowest eigenvalue. This is the eigenvalue of this again was -1/2. The other eigenfunction we had was rotation, and if you look at this guy, you realize it has precisely 1 0. On the arc, again at the top of the arc. You just have to look at the specific form of it. So the next eigenvalue is lambda r equals 0. And now I'm done. Because, well, any other eigenfunction, okay, you have to prove that in this setting the eigenfunctions are simple, but okay, that's essentially the compact thing I did before. So okay, then they are simple, and the next one must be positive. How positive? I don't care. Although I could estimate it if I put in a bit more work. And that's the sketch of the proof. Thank you for your attention.
Thank you. Are there questions or comments?
Hi, Theresa. First of all, thank you for a very nice result. I really appreciate it. So then the natural question it is if you also want to go to the last remaining unknown shrinker to
sure.
Stable,
sure.
linearly stable.
I still, so there is, you need a trick more. So the symmetry, the symmetry, the reduction due to symmetry ends up in the anti-symmetric case ends up more complicated, and somehow for the lens, I mentioned this picture. I didn't really draw it, so you look at phase space and you look at the curve that is v and then e to the gamma fourth v prime, and you parameterize in terms of lambda, and you look at some point, I don't know, t. If you increase lambda, this is going to rotate around the origin. That's the oscillation I meant. And for the lens, you only need to care about the angle. So the nice thing in this setting is that the angle equation is nonlinear, but the equation for how far you are away from the origin, that's a linear equation if you know the angle. So in principle, you could compute it, but that's complicated. For the lens, you don't need that because all you need is the angle. For the triple junction, that doesn't work anymore because you end up with a non-local, for antisymmetric, you end up with a non-local problem in the boundary values, and then you in order to know what your solution is doing here, you need to know what it's doing there. I have a trick that gets around this, but I didn't want to do that, and I still have to. But yeah, I mean, I'm trying to do all of them, actually. I mean, yes, I know the others are not as, but might as well do them all, right?
Okay. Other questions? Well, maybe I have a natural question, sure, possibly. Can you go from linear stability to non-linear stability? So if you start close in some sense to the lens, you singularize with the lens singularity, something like that. Or once you rescale, you go to the lens.
So the thing we're shooting for is we have linear stability. Next thing would be to prove that it's a local minimizer of your f or your lambda, or however you want to phrase it. Question is what does local minimizer mean? In which topology are you close? If you're close in a strong topology, that's not terribly hard. If you're say if you're doing the topology that corresponds to strong solutions of network flow, you're super close. You basically linearize, and it almost that works. Trickier is what happens when you're not close in, I don't know, C1 or W1 infinity. But so if you would want to have stability with respect to weak solutions, that's a lot more complicated. So yes, you can. Question is, how hard is it going to be, and in which sense do you mean it?
Okay, thank you. So if there are no other questions, we thank Theresa again. The next.
So the first speaker of this afternoon session is Alessandra Pluda from the University of Pisa. She will speak about geometric flows, monotonicity formulas, and geometric inequalities. Thank you.
So first of all, thank you, Giovanni, for the introduction, and thank you all the organizers, Giovanni, Roberta, Alice, and Matteo, for the invitation to give a talk here. It's always a great pleasure. And today it's my pleasure to present a result obtained in collaboration with two of my favorite people, in particular Luca Benatti, that was my former postdoc here in Pisa and is currently in Vienna, and Marco Pozzetta, that it's my academic brother and was also in Pisa at a certain point, and at the moment is in Milan at Politecnico. Okay, the paper is this one for the Pisa people that were here also 2 weeks ago. It's the same paper that Luca already explained at the conference in geometric analysis, but my talk is the complementary, so intersection almost empty. Because this paper is a technical result for a quite large family of monotonicity formula. And the general context of the paper are Riemannian manifold In particular, we consider an n-dimensional Riemannian manifold. We require the dimension to be greater or equal than 3. The manifold must be complete and non-compact. However, the setting of today's talks is simply going to be R3. So if you don't like manifold, this is not going to be an issue. Let me only advertise a little bit the paper. So this is a technical result. Is in some sense a different approach to monotonicity formula in nonlinear potential theory and inverse mean curvature flow. And what was particularly interesting for us are the applications. So in particular, in our family of monotonicity formula, we don't put any assumption on the curvature. However, if one restricts the vision to specific cases in which we put extra assumption on the curvature of the manifold, one can obtain geometric inequality. In particular, if one requires that we have a positive scalar curvature and the manifold as a boundary with certain hypotheses, then we can recover the so-called Riemannian-Penrose inequality that in the mathematical complete proof was first established by Wisken and Dillmanen with a considerable apport of information done also by Giovanni Bellettini, that is the one that noticed that there was the Gero community formula for the Hawking mass. And then recently, using instead of the inverse mean curvature flow nonlinear potential theory, this inequality has been reproven again by Agostiniani, Mantegazza, Mazzieri, Oronzio in 22. With this kind of method, there are clearly different methods and different proof of this result. For example, I want to state the one by Bray, that it is contemporary of this, but doesn't use this kind of method. So if instead we require a condition that is called the Ricci pinching of the manifold, with this technique, we are able to do a characterization of Ricci pinched non-compact manifolds, and we are able to prove that they are flat. And this is the result that we have obtained in collaboration with Venatti, Ariadna Leon Quiros, and Francesco Ronzio. And finally, that it is in some sense the main focus of today's talk, one can restrict to the case of Ricci positive manifold with a Euclidean volume growth, so with a property of how the balls grows at infinity. And under this kind of setting, one is able to prove the Wilmore inequality, or more general Wilmore type inequality, that with this method has been proved by Agostiniani, Fogagnolo, and Mazzieri, and also by Sederbaum, Kogo, Paulo dos Santos, and Leandro. And more in general, Minkowski type inequality, so an entire family that with this method has been first proved by Benatti, Fogagnolo, and Mazzieri. So basically, what our result does is put all of these results, here I also want to mention Wisken and Kerber, because it's the inverse mean curvature setting, under the same roof. And so basically, the monotonicity formula are manageable enough that if you restrict your manifold with these extra hypotheses, then you can obtain all the monotonicity formula that are crucial to prove all these results. So in some sense, it's like a unified point of view on these problems. Okay, so for today, I will restrict to the case of the Wilmore flow, of the Wilmore inequality. And my setting is going to be only R3, because instead of focusing exactly on the result, I prefer to focus on the method that are behind this result, because I think they are quite general and flexible and can be of a broad interest. And most of all, because I think that it's important in this community because it's crucial to pass from a strong solution flow to a weak flow. So I think it's really of interest in this community. So let me a little bit explain my title now and what I want to do now. So why monotonicity formula are crucial in geometric analysis, I think that we have all an idea of why. So for example, because from monotonicity formula, one can recover analytic property. For example, I think about regularity. And I want to state an example that is familiar to the audience is Allard regularity theory for stationary varifold. So one sees that when the monotonicity formula is there, then recovering the regularity is much simpler than when the monotonicity formula is not there. So in this setting, in the setting in which one is considered an RN setting with a standard metric and the standard norm, we know that monotonicity formula is crucial to prove regularity. On the other hand, monotonicity formula is also crucial to get geometric properties, and the two things are also related. And here I want to mention my favorite monotonicity formula that has already been mentioned this morning by Theresa, that is Whisker monotonicity formula for mean curvature flow. So what this formula does, the formula does two things together. One can say that under the assumption of be a type 1 singularity, they have some control on the curvature. So one can really get a limit of the scaled flow. And also, one can study the shape of the limit, because as we have seen this morning, self-shrinker appears naturally from the monotonicity formula in the case of the mean curvature flow. So what we are going to do now is, in this kind of context, starting from monotonicity formula, in the setting of nonlinear potential theory, and gain analytic property that in turn get us geometric properties, but then we also go back. So when we know extra regularity, we are able to recover a monotonicity formula in the case of the inverse mean curvature flow. So the entire idea of our paper is to try to close the circle between all these notions and how the geometry and the analysis can help each other to attain geometrical result. Okay, so this explains the part about monotonicity formula of my title. I would like also to enter in the connection between geometric flows and geometric inequalities. So there is a general strategy that allows to prove geometric functional inequality when there is a certain monotonicity of a quantity along the flow. So let me state the strategy. Suppose that we fix a class of objects. Let's say that our objects are hypersurfaces. With certain properties. And then consider f a functional, but it is a geometric functional defined in this class. Suppose, moreover, that we have a geometric flow. So what is a geometric flow? A geometric flow is a time-dependent family of surfaces in the class that evolve with a certain law. And what we can do with this? Okay, suppose that. So for example, if you think of a geometric flow, think, for example, of mean curvature flow, Wilmore flow, this kind of flow that are all familiar with the audience. And then suppose that we have three main properties. There exists a unique solution of the flow. And it is also global in time. So this maximal interval of existence is 0 plus infinity. Then suppose that the functional f is monotone along the flow. So that usually when does geometric flow, the first thing that one can try to do is compute the evolution of equation of geometric functional. So for example, let's compute with d in dt of f of nt, and suppose that it is less or equal than 0 or greater or equal than 0. And finally, suppose that we are able to produce a asymptotic analysis in the sense that we are able to see what happened in the flow when time goes to plus infinity. So in particular, suppose that we are able to produce the limit, in certain sense, as t that goes to plus infinity of nt. And suppose that this limit is n star. And then compute f of n star. This is going to be a certain constant, a central number. Then, if we put together these three things, we get for free a geometric inequality. Because what we are able to prove, if we put together 1, 2, 3, one is able to prove that for any n in the class where the flow was set, it holds that f of n is greater or equal than f of n star. Yes? Absolutely, yes. So this is such that here you have to put all the such that you need to carry this discussion. So this is the strategy, but then we are going to see specifically which kind of regularity one needs here. So in particular, the original strategy that has been performed by differential geometry for a very long time requires a strong solution, classical solution, C-infinity solution. So this is the big point of today's talk, what is there. So when you do like this, when you're able to prove that in this certain class in which you can have restriction due to regularity, but not only, also due to the effect to be mean convex, star shape, a lot of things, you have inequality. So, and the weaker is the class, the bigger is the class of competitor, and so the most significant is the inequality. No, not only, one also is able to recover what is called so-called rigidity. That means that one has an equality here if and only if n is equal to n star. So this requires clearly extra work. So this is the main strategy that allows us to connect geometric flows, geometric inequality, and crucially, monotonicity formula. So from these three things, we get a geometric inequality and rigidity. Most important for today's talk, I want to set my ambient space to be R3. But if here we allow a manifold, then a lot of time when we arrive here, we don't only have this kind of rigidity, but we have also double splitting. This means that not only one has equality if and only if this holds true, but also if the manifold is the model case. So this means that geometric flows are not only able to give you information about a certain functional, but also about the manifold. Okay, so today we have R3, so this is not there because we have already a fixed ambient manifold, so this is not going to be the case. But this is the main strategy of all this story. And clearly, one can try to reproduce this scheme in this kind of setting. As Julia was saying, one big issue is the regularity. That is going to appear here, but also here. To perform an asymptotic analysis, you all sometimes need a lot of regularities to see what happens at infinity, because not only you have to obtain a limit in a certain sense of this object, but you also need to compute the functional at infinity. So you need a lot of structure usually. And the other crucial thing is monotonicity. So it's not easy to find monotone quantities. Clearly, if we work in the class of gradient flow, we have a natural monotone quantity. However, that is like a bit of cheating. One would like to have something more general. So this is the strategy. This is what we want to do. And I'm going to explain the situation in the case of the Wilmore inequality in R3 that I'm going to state now. So I'm going with this example because the line of reasoning is somehow similar in all the situation, with clearly more difficulty in certain situation. And I decided to start with the simplest possible inequality here. So theorem, what I want to prove. Suppose that you have omega in R3. Suppose that omega is bounded, and also let's say smooth. Put the regularity that you want, says infinity. Then it holds this inequality, but it is exactly my Wilmore inequality. The integral over the boundary of omega of h square is greater or equal than 16 pi. Where for me, h is the sum of the principal curvature, not the mean. If not, I would have before. Okay, so this is the theorem that we want to prove. So this is the inequality we want to prove. And clearly one also would like to say that if you have equality, then you are the ball. And then I have to present to you the main character of all of this, because as I was stating here, I need a flow. So I need a geometric flow. And for today, my flow is going to be the inverse mean curvature flow. And I start with classical solution. So I suppose that I have, let F0 be a smooth immersion of n and hypersurfaces in R3. Then an inverse mean curvature flow is a time-dependent family Ft in a certain maximal time interval 0 capital T of immersions in 0T with datum F0 if there is a law, an evolution law that prescribes evolution that is in normal direction, that it is dt of f of Tp is equal to 1 of the curvature in the normal direction. So this is the outward normal. So the flow is expanding for all t in 0 capital T and for all p in n. And clearly we have to attain the initial datum. So this is the classical solution of inverse mean curvature flow. So for people that are familiar with the mean curvature flow, in that case, we have h here, and nu is the inward normal vector. So in the case of a mean curvature flow, if you consider a sphere, this is going to shrink to a point in finite time. This does the opposite. So if you consider a sphere, this is going to enlarge and occupy the entire space, and the flow is going to be for all time. So let's start with an example that are exactly expanding sphere. So if we are considering sphere, we are in the simpler setting of radially symmetric solution. So the problem, the inverse mean curvature flow reduces to an ODE. So a solution of inverse mean curvature flow in the case in which n is Sn minus 1. And let's say that immersion is this sphere with a radius R0. okay, okay, maybe this is n and this is n plus 1, if I follow my notation. So since we have a radial symmetric initial data, the flow is going to preserve this radially symmetric symmetry, and so we can reduce the PDE to equation only for the radius to describe the entire evolution. And so what we have the ODE, R prime of t, and then I have to compute the mean curvature, and then 1 over the mean curvature. So I'm going to have 1 over n R of t, and my initial data R0 is R0. So what we see from this example is that sphere remains sphere and are growing exponentially. So the solution for the radius is R of t, R0 e to 1 over n t. And t is going to be in 0 plus infinity. So this is an example of a global solution that exists for all time, doesn't develop any singularity, and the problem has been reduced to an ODE. Okay, so what we see, a sphere that remains a sphere become bigger and bigger. So for conveniency, for what is going to happen later, let me draw this solution, not in the space, but in the space-time. Suppose this is my slice of time t0, and this is my sphere. And then I want to draw the evolving sphere in R2 times R plus, but it is the time coordinate. So what I'm going to see sphere. So if I look at any time slice, I see like a bigger sphere. So this is the picture that one should have in mind. So why spheres are so crucial? Well, because spheres are the asymptotic behavior of the flow if we start with a very nice initial datum. So this is the theorem that says so. And it is a theorem of the 90s by Gerhard. And at the same time by Urbas. And what does the theorem say? The theorem said that let N0 be compact, smooth, strictly mean convex, in the sense that the curvature has to be strictly positive, star-shaped, and also important, n is an Rn plus 1. So the ambient manifold is the Euclidean space. Then the inverse mean curvature flow exists globally in time. So this means that our maximal time interval is going to be 0 plus infinity. It is unique. And eventually, NT becomes a round sphere, an expanding round sphere. So what does this mean? This means that even if we don't have exactly a sphere at the beginning, but we have something that it is not that different in the sense that the curvature is always positive and it is star shape, then we have a global solution that in the end for t that goes to plus infinity is going to become a sphere. So we have recovered already the asymptotic analysis over there. So for t that goes infinity, we have a sphere. So what we need now to prove our Wilmore inequality in such a context, the only thing that we are missing for 1, 2, 3 is 0.2. So the fact that integral of h square must be monotone. And this is actually the case. So we have an evolution equation that I'm going to compute here. I write it in general for with used to Riemann manifold, and then I cancel the Ricci in 1 second. So what we have, the dt of integral of h square, the sigma, is equal. So to perform this computation, you need to use the evolution equation for h, the evolution equation for the measure, in particular here the area, the dt of the area is the area, and the Bochner inequality at a certain point, but in this case is equality. this is equal to -2 tangential gradient of h squared divided by h squared minus second fundamental form square 2 plus h squared plus something that depends on the ambient manifold that it is reaching nunu. Then since I have set my argument in R3, this is 0. And then I use the definition of the mean curvature to be the trace of the second fundamental form to write that this is equal to -2 the integral of tangential gradient of h squared divided by h squared when I have a minus in front plus traceless second fundamental form square. So what is appearing here is not that important because, okay, there are geometric quantity, but what is important that they have manifestly less or equal than 0, which is what all we care. So believe me, one does this computation are somehow standard, one uses usual standard trick, Bochner and so on, and arrive to this formula. And what is important is that the identity of h squared is less or equal than 0. So now we have also recovered point 2. So we have 1 plus 3 under the hypothesis of strictly mean convex and star-shaped. Yes? Under the hypothesis that it is quite restrictive of H strictly positive and star-shaped. And then once we have the flow, we can compute this DNDT for every time. This strong setting, the flow is smooth, so all what is written here makes perfectly sense. So we have also 2. So the Wilmore functional is monotone. So what does this mean? Okay, this means that if we put everything together, we have exactly followed my strategy over there, and we have proven the Wilmore inequality in R3 under this hypothesis. Okay, this is already quite nice, but if you read the theorem, the hypotheses are not there. So what we are going to do now? One can say, okay, I try to extend this theorem. Suppose that I relax the hypothesis, I remove this hypothesis here. Can I still prove that the flow exists for all time? So because if one thinks of a proof of this, these are hypotheses that are there because they are quite convenient. Because if you have star-shaped and H positive, clearly the initial datum is well defined. Then you can prove that you can parameterize everything on a sphere with the H function, the H function. This means also that the equation reduced to a scalar equation for the distance, this distance function from the parameterization. And also one can prove that these 2 properties are preserved during the evolution. And so it's how one obtain this result. So, but one could think that these 2 hypotheses are only convenient to follow this idea of a proof. However, this is not actually the case because the flow actually develops singularity. So first of all, issue number 1, if the curvature of the initial datum is 0 somewhere, we cannot even write the flow. And even if we start with something nice, with curvature positive, the flow can develop singularity. So let's do an example of this to really convince you that this theory was already the best possible in the setting of classical solution. So if you consider something like a very thin torus in R3, so we have something like this. So when I do my cross section and I construct my thin torus, what does happen? It's possible to prove that there is a lower bound on the velocity because it's possible to prove an estimate for the curvature. One can prove something like that the maximum of H on NT is bounded by the maximum of H on N0 plus a constant. And so at some point, this flow develops point in which H is negative. or 0. Some point is 0, and then it's negative, and this means a singularity for our flow. So what can I do better than this? Other example, here you have a perfectly nice picture of the evolution of a sphere. Consider, for example, the evolution of two spheres. So at the very beginning, they don't interact with one another. So if one let go like a strong solution, so this become bigger and bigger. And then at some point they are going to touch. And again, here we have developed somewhere not positive curvature. So singularities are there also in the very simplest example. So really to go over this theory, one needs something else. Okay. Before to go in the weak solution setting, let me a little bit improve at least this. So what I told you is that doing asymptotic analysis often is quite tricky. It's not that easy because you need really a lot of regularity to take the limit to infinity. I would like to show a proof of the same argument that doesn't need the asymptotic analysis. So I think it's quite a nice trick. So let's do a proof of the Wilmore inequality without asymptotic analysis. What is the advantage of this proof? Not only this fact that there is no asymptotic analysis, but that the geometry of the ambient space is clear where to enter in the discussion. Okay, consider this proof. This version, let me call 2. So what can we prove? Okay, so this proof is gonna contradict the isoperimetric inequality. Okay, let me start with suppose by contradiction. That exists omega such that the integral over the boundary of omega of h squared is strictly smaller than 60 pi. And now I take this omega as initial datum of the flow. I consider the inverse mean curvature flow with datum omega. And okay, let me suppose it exists and that I can compute that I can do all the computation that I'm writing on the board right now. So let me start from computing the limit for t that goes to plus infinity of the volume divided by the area to the power 3/2. So I am doing this. My idea is that I will arrive to the end with a chain of inequality. I'm going to contradict the isoperimetric inequality. So we know that this is always less or equal than 1/6/√pi. So my aim is to contradict this using the flow and using the monotonicity of h squared. Okay, so what I do here, I do the L'Hopital. So this is greater or equal than limit. And then I have to compute d in dt of the volume. So d in dt of the volume is the velocity, 1/h. And then I have to compute d in dt of area. And this is a very nice property of the inverse mean curvature flow. The evolution of the area is the area. And we had already a glimpse of this when I told you that the sphere were expanding exponentially. So this is always the case, not only for the sphere. And so here I do my derivative and I obtain 3/2. And then I have the area to the power 3/2 minus 1 times the area, but it is the derivative, so it is the area. Okay, now it's moment to make our magic trick. So what we want to do now, keep in mind that we know the monotonicity of h squared. So from this object, we want to make appear an h squared. So here we have 1/h, we have to combine things to attain the h squared. And I do this by Hölder inequality. So let me write what is the area. So it's the integral of 1. And then I can write the integral of 1. And here I have conveniently wrote this in this version with a slice, so I can consider each slice a level set. So the gradient of the function 2 minus 2 over 3 times the gradient of the function times 2 over 3. And then here I use Hölder inequality. We conjugate exponent p equal 3 over 2 and q equal to 3. So I have the gradient of u to the minus 2 over 3 times 3 over 2 to the power 2 over 3 times the integral of the gradient of u to the power 2 over 3 times 3 to the power 1 over 3. And then I conveniently keep in mind that if I look in a level set approach, the gradient is the curvature, but I'm going to see this in 1 second. Give me only the time to finish my proof. And so what is this? This is equal to the integral of 1 over h to the power 2 over 3 times the integral of h squared to the power 1 over 3. And here in my proof, I have the 3 over 2. So here I need the 3 over 2. And so what I get, if I reverse the inequality, sorry, I'm able only to write less or equal. I'm not able to write greater or equal. If I reverse the inequality, I have the integral of 1 over h is greater or equal than the area to the power 3 over 2 divided by the integral of h squared to the power 1/2. Yes? I arrive. Give me 1 second. So if you imagine like this, you have to imagine that this picture that is given in R 2 times R plus, you can imagine like the slice, like a level set of a function, and u is the function. But I'm going to do the computation in 1 second. Okay, so I go on here and I have my inequality, and so I end up with the limit t that goes to plus infinity of what is remaining, only 2 divided by 3 integral of h squared to the power 1/2. And here I use the monotonicity. So I started with an object that adds h squared less than this quantity, and I have that the identity of h squared is negative. So also the limit object must satisfy the right equality. And so if we do the computation, here we have 1 over 6 of square root of pi. And this contradicts the supermetric inequality, and this is the proof. So what we have done with this trick, we have again used monotonicity. So this is necessary, it's not avoidable. But we have skipped asymptotic analysis. So what was crucial is still monotonicity. Well, okay, the existence of inverse mean curvature flow, because I suppose that I can do this chain of inequality for all times. And then crucial also the isoperimetric inequality. So this means that the geometry of the ambient space is appearing here with the isoperimetric inequality, and only here with a sign on the Ricci. If one has that Ricci is positive, when we are going in the right direction, this is minus, sorry. So this has also this advantage. What is the only disadvantage that we have? Okay, we have that still we have to compute this. So we need enough regularity to compute this function here. Okay, for the rest of my talk, I'm gonna speak about our contribution, but it's exactly how we can write that monotonicity formula in the setting of weak inverse mean curvature flow. So because we have understood that strong we cannot. So what we need a weak solution that preserves this chain of inequality. So what the only thing that we need is a weak solution that allows us still to write this inequality, even if it's not strongly defined. So, and to do this, we have to pass to the level set formulation. But I know there are a lot of people in the audience familiar with the parabolic level set formulation. My level set formulation is going to be an elliptic one. So I can also explain to you who was the U there in this definition, weak definition. Okay, so what I'm going to do, I'm going to suppose that my solution is given as a level set of a function. Okay, assume that the flow is given by the level set of U defined on R3 minus omega. Suppose that U is smooth. Okay, this is only for convenience in this computation. The gradient of U is different from 0. Clearly, we don't need this in reality. If not, we could not generalize the result. Okay, and so what it is that this f of t, my evolution is the boundary of omega t, and the omega t is given by the x such that U of x is less or equal than t. Boundary of omega t is given by the x such that U of x is equal to t. So I have my level set formulation. I have to end up with writing the equation. So what I have that t is equal to U of f of Tp. To write the equation, I want to use the flow, the fact that I have dt of f equal to normal divided by curvature. So I differentiate in time. So what I get here I get only 1. And here I have gradient of U dt of f. And now I use the fact that I have my flow equation. So this is equal to gradient of U times unit normal divided by the curvature. So let me write this curvature term over here. So I'm not dividing by 0. So if I look at the curvature of a level set, there is an explicit expression. It is the divergence of gradient of U divided with modulus of the gradient of U. So what I have here, I have gradient of U times the normal, but the normal to the level set is gradient of U divided modulus of the gradient of U. And so I end up with modulus of the gradient. And so what I have the 1 Laplacian of U equal to modulus of gradient. And this is the level set formulation of the inverse mean curvature flow. When, okay, I need the initial data. I suppose that U is equal 0 on the boundary of omega, and U goes to infinity in some sense as the distance goes to plus infinity. So I require some properness of the flow. Okay, so this is the flow, and I want to make you notice that this is not anymore a parabolic equation. This is an elliptic equation. So what can do now is to use all the knowledge on elliptic PDE. So there are still issues because so there is a non-standard existence and uniqueness theory for this flow that has been introduced by Wisken and Mannen. And the best bet we were able to get is that U is Lipschitz. And okay, if you look at the level set is C1, something. Okay, depends. So what you want to say. But clearly with Lipschitz, still we have a problem here. So it's true that H is not a second derivative because H is a modulo of U. So H is a first derivative. However, I'm taking another gradient. So I need a little bit extra regularity. And so what is a way to obtain this extra regularity is the p-harmonic approximation, or the p-inverse mean curvature flow. So we know that the one Laplacian is a very degenerate parabolic elliptic equation. So one can pass to p-inverse mean curvature flow and approximation. So this point of view has been proposed by Moser in 2007. So it's quite old, but has never been exploited to the maximum possible regularity theory. So what one does, instead of considering the one Laplacian, one considers the p Laplacian. What is the p Laplacian? Oh, let's say W. It is the divergence of the gradient of W to the power pi p minus 2 gradient of W. And then one puts this equal to gradient of W to the power P. And then it's quite reasonable that when P goes to 1, the solution of this equation goes to that 1. At least formally, one can believe it. And then one can also put equal 0 on the boundary, and W goes to plus infinity at infinity. So this is the P inverse mean curvature flow. And one here can use the entire theory of p-harmonic function. Why? Because UP, that it is the exponential or minus WP divided by P minus 1, is a p-harmonic. So existence theory and so on is completely get by this change of variable. And then there is the approximation theorem. So what was known before our result, Moser, 07, and Kochvar, Ni, 09, is that WP converge to W1 locally uniformly. That is not enough to obtain also the monotonicity, but we are also able to prove that the gradient of WP converge to the gradient in LQ for every Q less than infinity, and also that the level set converge in the sense of curvature varifold. So we also have that curvature goes to curvature, second fundamental form goes to second fundamental form. So what we need now to close the proof, okay, I have changed the flow. So it's really not possible that the functional is still monotone. So it would be a complete miracle that such a functional is going to be monotone along the level set a totally different flow. So what we need now it is construct an approximation, not only of a solution, but also the functional and the monotonicity. And how one can do this, even in the general setting of manifold, one can focus on the model case. So one consider initial datum, a ball, center in 0, and the space R3. And then the idea is to construct a proxy of H square that is monotone along the new flow, and that in some sense converge to H square when P goes to 1, and the derivative converges to the derivative. So how one does this, okay, we are in the model case of a radial setting. So if we are in the model case of a radial setting, we can compute explicitly the solution. So it's a ODE. And so what one gets is that WP is related, is a constant logarithm of R, where R is the distance function. And W1 is a constant logarithm of R, and there is a constant that put together these two things. And the constant are P over 3 divided by 2, 3 minus P divided by 2. So from this, what we can get, we can compute the gradient. So W1 is the solution of the inverse mean curvature flow. And what we keep in mind now that in the case of a inverse mean curvature flow, the gradient is h. So here I can go with an equal. And so what I can get, I can imagine that h divided by 2 minus the gradient of WP divided by minus P is a deficit. It's going to tell you how far you are from being an inverse mean curvature flow, in the case of P greater than 1, and also how far you are to be from the model, the very nice case of a sphere. And keep in mind that in the limit of the Wilmore, we see the sphere. The 16 pi, the rigidity is obtained by the sphere in the limit is t that goes to infinity. And this deficit is going to encode everything. So our functional fp is going to be nothing but the integral over the boundary of omega of h squared minus 4 for computational reason, h minus h divided by 2 minus the gradient divided by 3 minus p to the power 2. And so this is the monotone function in our proxy. So one can prove the convergence. And finally, one can compute the derivative of this guy here, because we have a little bit more regularity with respect to the inverse mean curvature flow. And what we are going to get, a minus, see there we have a 2 in front, here we have 3 minus p. So if I put p equal to 1, I get exactly what I want. And what I have here, I have tangential gradients of modulo of gradient square divided modulo of gradient square, and this is an h in the limit case. Then I have, again, my traceless second fundamental form square, and then I have my deficit, but it is going to be quite nasty, cannot be so easy, our life, because the deficit has in front a constant. It is going to degenerate when p goes to 1. So to prove that we have convergence with monotonicities, we need to have a very strong control of this object here. It's very refined because we have also the denominator that goes to 0. So what is going to tell you is that this object here is going to 0 very strongly in some sense, because it has to be a comparing between this, and finally one get this. So our result in some sense close the setting of something much more older than what we have done, but started with Wiskin-Hillmanen. So the idea was to prove this monotonicity and inequality for p equal to 1. So the ideal path is this one. However, there is not enough regularity to provide this monotonicity. So what Wiskin-Hillmanen did, they did an epsilon regularization and proved this. So they never get directly the monotonicity, but they have a regularized monotonicity. So this approach has been also performed by Agostiniani, Mazzieri, Mantegazza, Oronzio, in the sense that they have bring this to the nonlinear potential theory setting, this setting here. But to do this, they have a double approximation, p bigger than 1 and epsilon go to 0. So they are not able to get a monotonicity because there is epsilon around. We are going to send in here epsilon to 0, but they cannot. They have to keep it to have enough regularity everywhere. And so they do a quasi-monotonicity here. Then they send both things to 0 and 1, and they recover this path here. Then if you act quite smart, you can say, okay, I know that I need like the gradient of this object here, but let's not interpret this as an h. Let's simply write this as a gradient. So I don't have really true derivative. I don't need a setting in which you have really varifolds and curvature. And you do only an analytic interpretation, and you go directly to this monotonicity with a very clever cutoff procedure. And this is what Benatti, Fogagnolo, and Mazzieri did. But then we wanted, and then they go to the inequality, and then to the inequality for p equal to 1. But what we really want to do was to close this total setting and say, okay, you can do this, the things that you want. In particular, if we're able to have a geometric interpretation of a flow that is less regular, how it's not possible that we can have a geometric interpretation of a PEMCF. This is exactly what we did. We epsilon regularize here, and the epsilon regularization is only needed to attain the curvature. Here, when we work in the setting of varifold, it's a nice setting, which we can go directly here. So we have analytic and geometric interpretation of the flow. So also the PEMCF in some sense is a geometric flows. And then like this, we can do the way we want, because from here we are able to recover this. And so basically we close the circle, and this is our contribution. And thank you very much for your attention. Sorry, the acronym is too nice not to write. It's Beppo.
Thank you very much for the beautiful talk. Questions, comments?
Sorry, can you hear me?
Yeah, sure.
Hi, Liajun.
Hi, Alessandra. The camera didn't show the blackboard on the right hand. I mean, the online cannot see. Thank you. Okay. Okay, thank you. So one question is for the Vilmore inequality in the left in the blackboard. So what is the rigidity?
What is?
The rigidity. The
rigidity.
equality
Okay. So wait, in the blackboard I have only written the non-Riemannian one. If you want the interesting one, I think it's what is about the question is about. Let's put Ricci positive, and let's put greater or equal to 0 Ricci and avoir positive. Then here you have AVR, and the equality means that you are strictly auto-minimizing, strictly mean convex, and you have also the splitting. You split the manifold as a cone over the optimal. So you have a double splitting, also as in Minkowski. So the rigidity was already known in the paper by Agostiniani, Fogagnolo, and Mazzieri. In the case of the Wilmore, we have only improved it in the case of the Minkowski, in which the strictly mean convex was an assumption. We prove that it is coming from the equality. It is quite technical. So it's not only because, here up here the strictly mean convex hull. So it's a bit more complicated than that.
Okay, thank you. So this rigidity can also be obtained using the p-harmonic function, using this level set formulation.
Well, this is very interesting. So in some sense, you have something like this, but you don't have H. So you have, okay, you have to write you the quantity. Okay, give me 1 second. So you have to go here for the rigidity. And to prove that this is 0, this is, you have all the constant part. It's a bit more involved.
Okay. Thank
and
you.
clearly the inequality, the real inequality, the geometric one can be obtained only in the limit. So the inequality there, it's different. You're gonna see the P capacity and so on. So it's unavoidable.
Okay. Thank you. So
So
another
for
maybe
example, as in
naive.
the case of Chauchy and collaborator, they have also something like this.
Okay, thank you. So another maybe naive question for the Gerhardt and Huysken's inverse mean curvature flow. Actually, I mean, somebody can also consider, for example, the with free boundary case. So now everything here, omega is closed more or less. The boundary of the domain is closed half surfaces, but it also can define like the free boundary, for example, in compact hub surfaces with free boundary, and also you have the inverse mean curvature flow. And if the initial is star-shaped, strictly mean convex, then you can get some flowing smooth convergence. But I'm curious about for the weaker setting, for this level set formulation.
So,
Is there some...
I got your question. So the main difficulty there is to define what is strictly auto-minimizing in this weak setting. In particular, you need to define in a reasonable sense what is H equal to 0 in the P setting. And okay, this is quite something one has to take care about. And Okay, the only case in which we have considered the boundary case is, okay, clearly the Riemannian paradox, because there we need, and also the Ricci-Pinch manifolds. But there we have a negative result. We prove that there are none. But okay, so always in the limit. I have not considered a case with boundary P bigger and try to understand something.
Okay, okay. Thank you. Thank you very much. Thank you.
Other questions? Okay, if not, we can thank again Alessandra.
Thank you.
So it's my pleasure to introduce the second last speaker of this afternoon session, Giacomo Del Nin from the Max Planck Institute in Leipzig. He will speak about the gamma convergence of the square sticky disk to the octagonal crystalline perimeter. Thank you.
Okay, thank you. So thanks a lot for the opportunity of presenting this result here. I will talk about this joint project with Lucia De Luca. Yes, so it's about some variant of the let's say, classical problem of the sticky disk. So let me start with the general description of what's this problem. So we have a collection of n points in the plane, and we want to minimize some energy. That's very simple. It's just the pairwise, like the sum of all the pairwise interactions of all the points, where the energy depends on some potential V evaluated on the distance between the particles. And usually the potential V is some, let's say, attractive repulsive type potential like this one, where near zero you have some very strong repulsion, so particles do not want to go too close together. And then at infinity there's some, let's say asymptotically it goes to zero, and there's some minimum, so there's some kind of preferred distance between the particles. And yeah, so these are called also Lennard-Jones type potentials. Yeah, one of the questions that we can ask in this business is, for instance, if we can characterize minimizers for a fixed number of particles, or even if we can say something asymptotically as the number of particles goes to infinity. Okay, so maybe find some limiting problem in the sense of the gamma convergence, for instance. Okay, and what I will talk about is the sticky disk model, and let me start with the isotropic sticky disk, which is the standard one. So the point is choosing a potential V, which is like this. So it's a potential that's plus infinity between 0 and 1. So the particles do not want to go closer than 1 because otherwise the energy is plus infinity. Then there's they are strongly encouraged to be at distance exactly 1 because you gain -1, and then the potential is 0. And why it's called sticky disk? Because you can imagine to have disks of radius 1/2, and they do not overlap because the energy would be plus infinity, but they are strongly encouraged to be tangent to each other because there's a -1 in the energy. So this is why it's sticky. And in this case, this is exactly equivalent to counting the number with the minus sign, the number of tangencies between the disks. So this is a sort of very, very singular version of the Lennard-Jones type potentials, where you imagine to send this well to infinitely narrow, but it's already quite interesting. There's lots of questions that you can ask, and some of them are still open. So what you expect to see in this with this potential is to see some triangular patterns. This is maybe not surprising if you think about that. A particle with 6 neighbors at distance 1 is exactly sort of the optimal thing that you could build, because you have exactly all distance 1 and also distance 1 between the tangent, the neighboring particles. So this is what you expect to see, some sort of triangular pattern. And this was actually proved by Heitman and Radin in 1980, where they proved that minimizers are exactly crystallized. Namely, there is some rotation or translation of some lattice such that these minimizers are a subset of this lattice. And there's also some work on the more on the asymptotic side. So when you send the number of particles to infinity, concerning the global shape of this cluster, let's say. And it has been proven that for absolute minimizers, so global minimizers, this global shape converges to an hexagon. If you rescale everything so that everything is bounded, then minimizers converge to an hexagonal outer shape. And yeah, so instead of looking at minimizers, one could actually look at some more general, sequences. So you could also consider more generally low energy sequences, which are sequences that satisfy this inequality. So -6n is, let's say, the expected value so for every particle you expect a -6 in the optimal configuration. But you cannot have a configuration where every particle has 6 neighbors because there's some boundary effect. And so you will, in general, you will expect some extra term of order square root of n. And so you can decide, okay, I will consider sequences of xn, where n goes to infinity, so that satisfy this inequality for some uniform C, uniform in n. And I want to study the asymptotic behavior of what happens. And this also has been done in the case of this isotropic sticky disk. And there's I mentioned these two works by De Luca, Novago, Ponsiglione, and by Friedrich, Kreutz, and Schmidt, where they essentially prove that, okay, now if you consider low energy sequences, you do not expect a single lattice because you allow for some, more perimeter terms, let's say. So what you expect to see is, anyway, to see a certain number of zones where you have an almost constant orientation, let's say constant orientation, but there can be some interfaces between the different zones. So this is kind of what you expect to see. And if you send n to infinity, you obtain this polycrystalline structure. And this has been proven in the sense of gamma convergence, for instance. Okay, that's 2 words on the strategy. So how would you attack such a problem? It's usual to just consider the graph associated to these particles, where you put a vertex on every particle, and then you put an edge whenever 2 particles are at distance 1, because then that's when they activate the bond. And it's also usual to work with the so-called excess energy, where, okay, you can rewrite the total energy as this -6n, which is the ideal energy, which will be anyway there for your particles, but plus this sort of, let's call it boundary effect of due to all the particles that do not have 6 neighbors. So usually you forget about this because n is fixed, so this is fixed, and you consider this excess energy that in the end you can see that it's just counting the number of missing bonds. So it's 6 minus the degree of the vertex. And then once you have this, you want to relate it to some kind of perimeter term. I mean, this is some sort of discretized perimeter, but you want to associate it to some more continuous perimeter and then pass to the limit to obtain some continuous perimeter. Okay, this was about the isotropic sticky disk, which is the, let's say, the standard, the classical version. What we consider with Lucia is an anisotropic version, where we consider the L-infinity norm in the plane. So, I mean, the maximum between the 2 coordinates. So the energy is the same, but now also the potential is still the same. But now the distance is not the Euclidean one, but the L-infinity one. And so here you see that if you play a bit with the energy, what you expect to see is qualitatively different, because you expect, like, this is the ideal configuration where you have one central point, let's say, and then you have now, instead of 6, you have 8 neighbors, all at distance, anisotropic distance 1. So also these are L-infinity distance 1, right? And you can actually prove that this is the only way of putting 8 neighbors around a single particle. So it's very rigid. And so in this case, what is natural to look at is low energy sequences, where now you put a -8 here, which is the bulk energy of the configurations. Okay, 2 words about why exactly the L infinity norm and not other norms. So one could use other norms, but there's this specificity in the plane that essentially the L infinity norm, or let's say affine copies of the L infinity norm, so norms that whose unit ball is a parallelogram, are the only ones that are qualitatively different, because for any other norm, you still have this 6 neighbor property. And this is related to the fact that, so if you consider in the isotropic case, you have one disk, you can put 6 disks around the central one, and all of them are tangent to each other. And the surprising thing is that you can do the same with any symmetric convex body in the plane. At least it was surprising to me when I discovered this. So you think, and there's also so you see that all of them are tangent to the central one, but also to the next one. So there's no wiggle room. And you can also, you have a 1 parameter family of such configurations where you can slide all of them around. I mean, you cannot rotate them now because you have some fixed shape, let's say, but you can still slide them around. And the parallelograms are the only ones that at some point allow for the vertices to touch, so to create 8 neighbors, not just 6. So what's, let's see very briefly, what's some advantages and disadvantages of this with respect to the isotropic case. So the advantage is that a particle with the maximum number of neighbors, in this case, is very rigid. So in the isotropic case, you have this rotational freedom, and you still have 6 neighbors. In this case, with the L infinity distance, you only have the situation is very rigid. So the one I showed you before was the only one, the only configuration where you can have 8 neighbors around. And so this indicates that there is no polycrystalline structure when you look at low energy sequences, but you're likely to see just a single crystal due to this fact. So this single crystal structure is kind of an advantage because it makes the situation simpler. But what are some difficulties? That first the aim is to prove a full gamma convergence result without any constraint. So which is usually a hard task. At least for the isotropic case, it was quite a challenge. And then another difficulty is that if you want to sort of attack this problem with the graph theory, then in this case, if you take the bond graph, so you put vertices on particles and then edges whenever 2 particles are distance 1, now this graph is not planar anymore. So it makes the situation a bit more involved from the, let's say, combinatorial point of view. But however, the only non-planarity actually of this graph comes exactly from the crystallized configuration where you have these 8 particles around. So in a way, there is some non-planarity, but it's still tame, meaning that you know exactly what happens when you have non-planarity. And the goals that we have are, well, usually, as in these problems, the first is crystallization, namely you fix the number of particles and you want to show that your minima are a subset of some lattice. In this case, the square lattice is the natural one. And there's actually a very elegant proof by Brass that you can always find one minimizer, which is crystallized, so a subset of the square lattice. But then he doesn't really prove that all minimizers are crystallized, and we do this with Lucia, but it's the idea is very clear somehow, but the details are more involved. And then the second result that you want to show is some gamma convergence, so some limiting process when the number of particles go to infinity. And this is actually the topic I want to focus on. So I won't talk about the crystallization, and I focus on the gamma convergence. Okay. So first, before going to the result, I mean, I will need to talk about anisotropic perimeter. So let me just recall what is an anisotropic perimeter, also just for the notation. So usually, I mean, of course, you have the perimeter, which is the integral of 1 on the boundary. And the anisotropic perimeter is just the same, but where you fix some function phi of the normal, and so you integrate that function phi on the boundary. So phi is some function that goes from S1, let's say, to R, and it's called the anisotropy. Okay, so what is the main result? I need to introduce some renormalized functionals. So as I told you, the energy E is the sum of all the interactions, but we are interested in the excess energy, which is when we add this term A10. So this is like the excess energy, as I defined before. And so we define this energy that on the, like for fixed M, gives you exactly this excess energy if the configuration has n points and otherwise it's plus infinity. And then we want to consider this very specific anisotropic perimeter, where the anisotropy phi is given by the sum of these 4 terms. So the phi of some unit vector with coordinates nu1, nu2 is the sum of the moduli of nu1, of nu2, of nu1 plus nu2, and nu1 minus nu2. And this is the Wolf shape associated to this anisotropy, meaning this is the isoperimetric set for this perimeter. And here, this is not the regular, I mean, it is the regular octagon, but regular with respect to the anisotropic distance. So this is Euclidean distance, I mean, the Euclidean length is 1 and root of 2. Okay, so this is, yeah. And the main result is that we prove that a suitable rescaling of this excess energy, so where you rescale by the root of n, which is the natural rescaling, these functions gamma converge to this exact anisotropic perimeter here. Okay, if you talk about gamma convergence, you should first define what is the convergence that you consider. So in our case, there's many choices. You can have in mind the following one. So you have your configuration xn, and then you take the measure, the atomic measure that's naturally associated to it. So it's this rescaled probability measure where you put a delta in each, actually in each xi, but also where you rescale the domain by root of n so that everything stays bounded. And then you renormalize by, so that the total mass is 1. And so whenever you have a sequence xn, you say that this sequence converges to some set. Okay, if the associated empirical measures, or these ones, converge to the characteristic function of this set. So in the sense of measures, for instance. And okay, so the gamma convergence is a kind of functional convergence, you know, for functionals. But the actual difficult part is showing the gamma limit, called gamma limit inequality. So what we need to show, and the difficult part is showing this, that whenever you have some sequence xn that in this sense converges to some set A, then you have lower semi-continuity of this anisotropic energy compared to the discrete energies. So you have the gamma limit inequality. Okay, just a picture so what should you expect for such configurations? This is kind of what you would expect. So there's some particles that are very happy. They have all 8 neighbors. And in this case, the configuration is very, very rigid. It's just vertical, horizontal, and diagonal edges like this. And then, however, you can have some particles that have less neighbors, some that only have 1 So this is what you see, that whenever it's basically almost a planar graph, but it's non-planar only when you have these square faces. And what is the strategy to relate this? I mean, to prove the result is relating the discrete energy, so the missing bond energy, to some anisotropic perimeter, some sort of perimeter of this configuration, and then use the lower semi-continuity of the perimeter. So the main part is to understand what is the set that you want to associate with these discrete points, and what is the relation between discrete energy and some perimeter energy of this set associated to this. Okay, first, also we have a related compactness result that tells us that this convergence is very natural. So whenever we have a low energy sequence, we can prove that the sequence converges in this, for instance, the empirical measures converge to the set. Even though, I mean, we need a slightly more refined convergence. So for instance, one can choose to do the following thing. So whenever you have some discrete configuration, you associate to it the set of all the square faces, like the square crystallized faces. In this case, it will be this part here plus all this part here. And so you have now a subset of the plane, and what you can show is that actually also this is converging in L1, at least locally, to the same set. So there's not a big difference between the empirical measure, which is the sum of deltas, and the sort of spread out measure on this union of square faces. They converge to the same limit. So you can use any of the two, either. And so, yeah, we have compactness, namely that if we consider low energy sequences, then up to subsequences and rigid motions, we have the convergence of this set, this rescaled set associated to the discrete configuration, to some finite perimeter set A. And the proof is very easy, because essentially the energy is counting the number of missing bonds. So whenever you have some missing bond, you can show that there is you must find some perimeter of the union of this set AN. So it's basically just an application of the compactness for finite perimeter sets. Okay, one word about why exactly you expect this anisotropy, which is, I recall, the sum of these four terms. And whenever you have such discrete problems, a way to guess what is the anisotropy is the following: that you fix some, let's say, a line with certain direction, with certain normal nu. And then, since you're counting the missing bond energy, you start counting what is the average number of missing bonds per unit length on the interface. And it's very, I mean, it's easier to do it if you separate the bonds according to the direction of the missing bonds. So horizontal, vertical, diagonal in this direction, and diagonal in the other direction. And this is just some planar geometry with trigonometry. You can actually compute that each separate contribution is exactly given by these pieces here. And so the total number is just the sum of this. And this is basically also the proof of the gamma-lim sup inequality for the gamma convergence, because it's exactly this argument plus, let's say, the density of polygonal sets in the set of finite perimeter. But it's basically this argument here. And the hardest part is to prove the gamma-lim inequality. So it's the other one. Okay, so again, we want to prove the following: that if we consider the set that I call, we start with the configuration, we take all the union of the crystallized faces, we rescale, we assume that this converges to some set, and we want to show the gamma-lim inequality, so that the anisotropic perimeter of the limit is less than the limit of this discrete energy. And again, the strategy is to find the correct set to associate to Xn, so that this discrete energy relates to the anisotropic perimeter. And we need we need a good choice for this set, because a very naive choice would be, okay, let's just take these sets AN, so the union of the square faces. But this is, if you do this, you cannot, this is too rough. This would work for the for an energy that only counts the horizontal and vertical neighbors, but not the diagonal ones. So somehow this is too rough. But also one other very naive choice would be to take, okay, the union of all the faces. But this is also not the correct thing if you think about, for instance, in this case, you have an annulus. So imagine that you have a configuration sequence that is converging to some set which is an annulus. So there's a hole in the middle. So if you take as a set also this inner face, you're not converging to the correct set. So you're not converging to the limit of the empirical measures. So somehow you have to choose to give a good choice for this set to associate to the discrete configuration. And how we choose this set comes from a so-called energy decomposition, similar to the one that Lucia proved with Gero-Frieseke. Okay, so the point is to find what is the correct choice for this set, and the idea is to find some energy decomposition. Now, what is an energy decomposition? This is the part that I'm going to explain now. So again, similar to what Lucia did with the Gero-Frieseke. And so the idea is to find a way of rewriting your discrete energy in terms of some combinatorial features of the graph. So we start from some graph in the plane where every vertex has degree at maximum 8, and where the graph is planar with the exception only of quadrilateral faces with both diagonals, which is exactly the situation that we see. And let's say the key quantity is the notion of this angular defect. So whenever we have an angle, alpha, we can define the defect, delta of alpha, as simply the amount by which alpha exceeds pi over 4. And this is rescaled, so that it's basically giving you how many multiples of pi over 4 you're exceeding it by. So for instance, pi over 4 has defect 0, pi over 2 has defect 1, etc. But you can also have, non-integer values. So this holds for any angle. And okay, if you look at graphs coming from the square sticky disk, so this anisotropic sticky disk, you can actually show that every single angle is bigger or equal to than pi over 4. So all these defects are non-negative. And somehow the key insight, which is actually very trivial, but allows you to change the point of view, is to notice that if the total energy is the sum of the missing bonds for every vertex. So it's 8 minus the degree of the vertex. And the point is that this energy, so 8 minus the degree, is exactly the sum of all the defects of the angles appearing around the vertex. This is just some very basic computation. And now, however, this allows you to do a double counting and see the total energy in a different way, because now what you can imagine is that you can also define the defect of a face as, let's say, you have this face, the gray one. You take all the angles, the interior angles, and you sum the defects at these angles. So for instance, if you have a crystallized square, then the defect is 0 because the inner angles are all pi over 4. If you have a triangle, then the defect is 1, etc., etc. And now, however, you can do the double counting. So the total energy is the sum of all the angular defects among vertices. But you can say, okay, now I sum among all the faces. So I need to include all the angles, but instead of summing among vertices, I sum among the faces. And this is essentially what you conclude, that the total energy that you're interested in is the sum of the defect of every face, including also the exterior one. Okay, just to have an idea of kind of what is the defect of a face. So again, here, imagine that you have all these angles, alpha I, the inner angles of the face, and you want to sum this defect. Now you can actually apply Gauss-Bonnet, and you discover that this only depends on the number of sides of your face, if it is simple, like in this case. And you get 3 times the number of sides on the boundary, -8. And the -8, I mean, it becomes a +8 if you're counting the exterior face, because you're going the opposite direction. And so more in general, if you have such a face with some holes and some components, you can sum all these estimates, and you discover that the effect of a face is basically 3 times what we call the combinatorial perimeter of F, so the number of sides appearing in the boundary. Then you have a -8, which is always there, which is the exterior component, and the +8 for every interior component of the face. In this case, I mean, the interior components are only 2, because you count basically the connected components of the edges. So in this case, it's only 2. Okay, now how do you, I mean, what is the energy decomposition? It works in this way. So it's actually a family of different energy decompositions based on the selection of faces that you make. So you start by selecting some subset S of the faces, so a subset of all the faces, but that contains all the crystallized square ones. And you take the union of all these faces. So for instance, here I chose like all these faces, but I didn't choose the whole. And then essentially you can prove that, again, you see the total energy as the sum of the defects of all the faces. You can split the faces in between the which that you chose and the which that you didn't choose. You substitute the expression with Gauss-Bonnet, and you arrive at the final result, which is the following. So again, let's fix some choice of some selection of the faces, which is this S. Then we can always rewrite the total energy of the configuration as the sum of some terms, combinatorial terms. Now, forget about these ones already, because we will just need some inequality. These are just positive, so we don't need them. But what we need is this inequality here, essentially. And what is appearing on the right-hand side is first the combinatorial perimeter of this union, so the number of boundary edges. Then there's a sum of the defects of the faces that we selected. And then there's a -8 times the cardinality of the faces that we did not select. Okay. So again, in this case, the union, the associated set is just the union of all these faces minus this whole. Okay, so some remarks is that, okay, for every choice of S, we obtain a different decomposition. And the key thing will be to find the correct S to apply this theorem to. And also that a similar proof works for, in the case of, let's say, the isotropic sticky disk, for graphs with maximum degree 6. And this gives us also the energy composition that Lucia and Gero-Friesike obtained. So now, how do we use this inequality? So here I just rewrote the inequality that we have. And the idea, as I told you, is to prove the gamma limit inequality, you want to relate the discrete energy, which is this F, to the anisotropic perimeter with the anisotropy that I wrote down of the associated set. So at the right-hand side, we would be very happy if we had the exactly P phi, so the anisotropic perimeter of this associated set AS. Instead, we have the sum of 3 terms. Okay, so, and one of them also has a negative sign, so it plays against us. So if we look at the perimeter term, how far is it from the actual P phi, so the anisotropy? Now, if you do the computation, you discover that P phi gives perimeter 3 with a weight 3 to every horizontal and vertical edge. So these edges you're counting with the right multiplicity already, so it's fine. But it gives weight 4 to edges that are, for instance, at 45 degrees. So this inequality is not good enough in this case because you would like to have a 4 for all the other edges. And what is the idea is, well, to get help from these defects, and show that these two together combined will give you exactly the anisotropic perimeter. And this is actually exactly what happens. So it's basically, the idea is that whenever you have some diagonal edge, you must have some defective face because it cannot be a square with a crystallized square. And so basically this shows that you can put together the first two terms and all of them together combined, they give you at least the estimate from above the anisotropic perimeter. So in the end, what you conclude is that your discrete energy, excess energy, f of x, will bound from below the anisotropic perimeter, which would be the correct thing. So, I mean, if you didn't have this term, this cardinality, you would be already happy, but you have this also this -8 that plays against you. So, I mean, just to get an idea, so if you select all the faces, then this would not be there. So, but selecting all the faces is too rough because you're not converging to the same set anymore. So you have to play with this fact of selecting the correct number of faces somehow. And how do you make this choice? Okay, so here I just rescaled by 1/√n. So you see this is the actual excess energy that we have. This is the anisotropic perimeter of some set depending on the selection of the faces, and you have this minus this negative term. How can you get rid of the negative term? Well, you just need to choose the faces so that this is small o of √n. But how do you make the selection? And what works is that you should take all the faces with sufficiently low perimeter. So let's say that we fix some beta, which is strictly less than 1/2. And we choose as the collection of faces, all the faces that have perimeter less than n to the beta. Now, these are the small faces because, I mean, if you had beta equals 1/2, you would allow for faces with perimeter √n, which is very, like, even when you rescale, it gives you some, some face that is not going to 0. So essentially, we are selecting all the faces that have perimeter, small o of √n, and we take the corresponding union. And the point is that you can show that with this choice, you still have the right convergence. So you have, for instance, in the annulus case that I told you before, this selection does not select the inner face because that would be a face with the perimeter of order √n. So in this case, with this selection, you're getting rid of, I mean, you're kind of making a good selection because you're still converging to the same set as before. And you can estimate the number of the faces that you did not select that are, I mean, will go into this term that's playing against you. So essentially by Chebyshev, you can see that the total cardinality of the faces that you did not select is bounded by some power strictly less than 1/2. So this is really some small o of √n. In this case, this means that asymptotically this is going to 0. Okay. I mean, okay, this is the actual computation, but I'll skip it also because it's the last talk of the afternoon. So let me just give you a summary of what is our result. So we consider this anisotropic variant of the sticky disk, where we evaluate distances with the L infinity norm. And we consider the total energy, which is the sum of the pairwise interactions. Then we show compactness for low energy sequences that are sequences that satisfy this inequality. Okay. And compactness in the correct, for instance, in the sense of empirical measures. then we prove the gamma convergence result of the suitably rescaled functionals to the anisotropic perimeter with the octagonal wolf shape. So this in particular proves that if you take minimizers of this discrete energy, they will converge after rescaling to some hexagon with sides 1 and root of 2. Okay, in order to prove the gamma Lie-Minf in particular, which is the hard part, we show an energy decomposition a la De Luca-Frieseke for a certain class of graphs in the plane. And somehow the key quantity that allows for this decomposition is this notion of angular defect that seems quite flexible. So it's hopefully it could be adapted to also other cases. Okay, and I'll end with some questions and open problems. So exactly, since the energy decomposition that we prove is kind of combinatorial, topological in a way, it could be hopefully used to attack other problems that are not exactly the anisotropic sticky disk. So for instance, one could ask if there is some proof of the gamma convergence even for the isotropic sticky disk using this energy decomposition, but in the case of the isotropic sticky disk. Or for instance, one could consider some slightly different potentials. So here we have, you can imagine to have the same type of energy, pairwise interaction, and having a potential that's plus infinity between 0 and 1. Then it's, instead of being -1 only at a point, there's a whole interval where it is -1, so between 1 and root of 2, and then it is 0. And then you evaluate, you use the same energy, but still with the Euclidean distance. But now the point is that even if you use the Euclidean distance, now you're also seeing the diagonals of the squares, because you have -1 between 1 and root of 2. So this energy still favors square lattices. And this has been proven, at least in a sort of thermodynamic limit by Betterman, De Luca, and Petracche. But one could, for instance, ask if there is some also gamma convergence in this problem, and hopefully maybe use this decomposition to prove it. And then, okay, I didn't write it, but also higher dimensional generalization. So instead of the plane, like 3D space, what happens? For the isotropic case, it's super complicated. But maybe if you put some anisotropy, there you have sufficient rigidity to still conclude some gamma convergence and say something. Okay, so I end here. Thank you for your attention.
Thank you a lot for the beautiful talk. Are there questions? Comments? Yes.
So there are these fun materials called shape memory alloys, which they have a temperature dependence in the crystal structures that they want, and so what happens is for high temperature you have cubic or square, and it degenerates as you lower temperature. It degenerates into these into these. It gets longer in one direction, shorter in the others. Can you do something similar here? So if you say you let the particles choose, don't take. I mean, don't take. You still have some isotrope. You still treat the two directions the same, right? Now, could you go into a situation where one direction is longer than the other one, and let the particles choose which of the two at once?
I'm not sure I got the question. So it's, you would like to put some different sort of optimal length in the two directions.
Yes.
And
then find a way of making the material, and making the particles choose which one they want.
To be honest, I don't know. Yeah, because I mean the thing is that this you can also just if you just rescale this functional like.
No, I mean then the point would be, you know, you could have both at the same time, and the question, you know, the fun part is figuring out when is it long in the one direction and when is it long in the other direction, and you get patterns that way.
Okay. I mean, I don't see a way of doing that immediately right now, but yeah.
But there's, you know, yeah, we can talk about that later if you want, but thank you.
So thanks for your talk. I understood correctly that you say there is just your gamma limit is a single crystal, and I understand that well, there are no rotations, so there is no necessity of introducing a polycrystal. But you could also have micro translations, which are on a little bit of a shift, which is smaller than the lattice spacing.
Yes.
Could you take that into account as well?
So I mean, that's kind of implicitly taken into account in this result by showing that somehow that's never convenient, yeah, to have this micro translation. So I mean, you can actually have low energy sequences which have this micro translation, but then somehow it's always more convenient to just not have them. So I mean, in a way, it's different from the isotropic case, where you really see these micro translations in the gamma limit. I think maybe it's a good feature of this problem that there's a simplification, and basically these micro translations they're completely forgotten in the limit. So at least for the first order gamma limit, they're not appearing simply. Yeah.
Other questions? I have yeah, also. No, yeah.
Just a curiosity, what is expected gamma limit in 3D if you do the same cube with the cubes?
I mean, if you suppose a priori that your particles are the subset of, let's say, Z3, then I'm not sure of the actual shape, but it's computable explicitly. It would, if you want, should be the Minkowski sum of all the bonds activated by this. How many? 26 directions, or in the but the difficult part is showing that you're a subset of Z3, or for the gamma limit, you don't. That's not even true if you consider low energy sequences. So it would be the hard part would be to show that somehow still in the limit this is true. But but I expect this sort of, I don't even know what would be the polyhedron, but it's actually computable very explicitly.
Okay. So if I remember correctly, one of the problem with the three-dimensional case in the usual setting is that it's true you can put 12 balls tangent to a ball of radius 1 and not in, but this is not rigid, and the non-rigidity makes the problem more complicated.
Yeah.
Now, if you have a situation, so are you telling us that if you have a situation where this type of basic problem has a rigid solution, then you have a nice gamma limit, and so is that what could be true in a higher dimension?
That's what could help you, but I'm not claiming that that's enough to conclude the gamma limit. But I'm saying that this rigidity should help you, for instance, telling you that there's only one crystal and making things simpler. But I'm not claiming that once you have that, you have the result, because you still have these micro translations, as Maru was saying. Like you're not necessarily in a single lattice, but you can have different lattices translated. And in 3D, it's still true that you have only one rigid configuration with the whenever you have the maximum number of bonds, you're really in this rigid configuration with the cube and all the cubes around.
Okay.
But passing from that to, I mean, there's some combinatorial argument that you should like this energy decomposition in the plane is, you can do it with some formulas for graphs, but in the 3D space becomes already more complicated. So, but should help. Yeah.
No more questions? Okay. Thank you again. We thank all the speakers of today.